Welcome to Triune Biblical University Global Extension USA channel. We are thrilled to welcome back our returning subscribers and extend a warm greeting to all our new viewers. Whether you're revisiting us for more knowledge or joining us for the first time, we're excited to have you here with us today. At Triune Biblical University Global Extension USA, we're dedicated to providing enriching educational content that empowers you to grow and excel. Your continuous support and engagement motivate us to bring you the best of our learning resources. Today's lecture, Advanced Structural Analysis. In today's session, we dive deep into the world of advanced structural analysis, a critical field for engineers and architects looking to push the boundaries of structural design and safety. Whether you're a student or a professional, this lecture will offer valuable insights into advanced methods and techniques that shape the way we analyze and design structures. So, sit back, relax, and prepare to explore complex concepts that will enhance your understanding of structural systems and their behavior under various forces and conditions. We hope you find today's lecture both informative and engaging. Let's get started. 8. Influence lines for moving loads. Principles of influence lines. Influence lines are a powerful tool used in structural analysis to determine how the internal forces, such as bending moments, shear forces, or axial forces, at a specific location in a structure change as a moving load passes over it. They are particularly useful in the analysis of structures subjected to moving loads, such as bridges and highways, where loads are not static but instead traverse along a structure. The influence line represents the variation of a particular internal force at a point on the structure as a unit load moves across the entire span of the structure. It shows how that internal force varies depending on the position of the load. 8.1. What is an influence line? An influence line is a graphical representation of how an internal force, e.g., shear, bending moment, or axial force, at a specific point in a structure varies as a unit load, typically represented as a 1-unit concentrated load, moves along the structure. The internal force of interest is calculated at various positions of the moving load. Influence lines are typically used for bending moments at specific points on beams, shear forces at points along beams or frames, reactions at supports. Influence lines are especially useful in the design of bridges, where vehicles or trains move along the structure, and the location of the load significantly affects the internal forces within the structure. 8.2. Key characteristics of influence lines. 1. Unit load. Influence lines are based on a unit load, typically 1 or 1 pound, applied at different positions along the span of the structure. 2. Variable internal forces. The internal forces, moment, shear, or reaction, are computed for the unit load at various positions along the structure, leading to a curve that shows how these forces change as the load moves. 3. Shape of the influence line. The shape of the influence line will vary depending on the type of structure and the location of the internal force being analyzed. For example, for simply supported beams, the influence line for the reaction at a support is a straight line. For bending moments in simple beams, the influence line may have a triangular shape. 4. Critical load positions. The influence line helps identify the positions of the moving load where the internal force, e.g., moment or shear, is maximized. This is crucial for structural design, as engineers can use these positions to calculate the worst-case scenario for loads applied on the structure. 8.3. How influence lines are developed. The procedure for developing an influence line for a particular internal force generally follows these steps. 1. Choose a location for the internal force. First, identify the point where you wish to evaluate the internal force, e.g., a bending moment at midspin or a shear force at a particular point on the beam. 2. Apply a unit load. A unit load, usually 1 or 1 pound, is applied at various positions along the structure. 3. Calculate the internal force for each load position. For each position of the unit load, calculate the internal force, bending moment, shear force, or reaction at the chosen location. 4. Plot the influence line. Once you have calculated the internal forces for different positions of the unit load, plot the results on a graph. The x-axis represents the position of the moving load along the structure, and the y-axis represents the value of the internal force at the point of interest. 8.4. Examples of influence lines for common structural components. 8.4.1. Influence line for reactions. Consider a simply supported beam with 2 supports at each end. If a unit load moves across the beam, the reactions at the supports change. The influence line for a reaction at one of the supports can be obtained by placing the unit load at various points along the beam and calculating the reaction at that support. At the left support, the influence line for the reaction is a straight line, increasing from 0 at the left end to 1 at the right end. This indicates that the reaction at the left support is maximized when the load is placed at the right end of the beam. 8.4.2. Influence line for shear forces. In a simply supported beam, the shear force influence line at a specific point can be plotted by calculating the shear force at that point as the unit load moves across the beam. The shape of the influence line for shear forces is typically linear and depends on the location of the point. For example, for a beam with a unit load placed to the left of the point of interest, the shear force will increase, and as the unit load moves past the point, the shear force will decrease. 8.4.3. Influence line for bending moments. For a simply supported beam, the bending moment influence line at a specific point on the beam is often triangular. The maximum bending moment occurs when the unit load is placed at or near the point of interest, and the magnitude of the moment decreases as the load moves further away. For example, at the midpoint of a simply supported beam, the influence line for the bending moment is a triangle, peaking when the unit load is at the midpoint and decreasing towards the supports. 8.4.4. Influence line for point loads on continuous beams. For continuous beams, beams supported at multiple points, the influence line can be more complex. The influence line for a bending moment in a continuous beam shows the variation of the bending moment at a particular location as a unit load moves across the beam. 8.5. Applications of influence lines. Influence lines are widely used in structural engineering, particularly for the design of structures subjected to moving loads. Some applications include: 1. Bridge design. Influence lines are essential in bridge design, as vehicles or trains move along the span. The influence line helps determine the maximum bending moments, shear forces, and reactions at various points of the bridge when a moving load crosses. 2. Railroad tracks. Similar to bridges, the influence lines help in designing railroad tracks, where the train positions will change during operation, affecting the internal forces in the track structure. 3. Highway overpasses. For overpasses or other structures with vehicular loads, influence lines help assess the worst-case internal forces and ensure that the structure can handle dynamic loads. 4. Towers and cranes. Influence lines are used to analyze the forces in tower cranes or other movable equipment where loads may change position over time. 5. Load testing. Influence lines are also used to predict and analyze how structures behave under dynamic loads, helping engineers design for safety under the worst possible loading conditions. 8.6. Practical example. Influence line for a simply supported beam. Consider a simply supported beam with a span of 10 m. We want to determine the influence line for the bending moment at the midpoint of the beam. Step-by-step process. 1. Apply a unit load at various points along the span, e.g., at 1 m intervals. 2. Calculate the bending moment at the midpoint for each position of the load. 3. Plot the results. The influence line for the bending moment will show a triangular shape, with the highest bending moment occurring when the unit load is at the midpoint. Influence lines are a powerful and essential tool in the analysis of structures subjected to moving loads. By providing a visual representation of how internal forces change with the position of the load, influence lines help engineers design more efficient and safer structures. They are crucial for designing bridges, overpasses, and other structures where dynamic loads vary over time, enabling engineers to predict the worst-case scenarios and ensure the structure performs optimally under real-world conditions. 8. Influence lines for moving loads. Determining influence lines for beams and frames. Influence lines are essential tools used to determine how internal forces in a structural element, like shear forces, bending moments, or reactions, change as a moving load travels across a beam, frame, or other structure. They are particularly useful in the analysis of beams and frames subjected to moving loads such as vehicles, trains, or cranes. This section explains how to determine influence lines for beams and frames, using a systematic approach. 8.1. Overview of influence lines for beams and frames. For a given structure, an influence line represents the variation in an internal force, shear, bending moment, or reaction, at a particular location in the structure as a unit load moves along the structure. Influence lines are crucial for determining the worst-case internal forces when dynamic loads, like vehicles, move across a structure. There are two main types of influence lines. 1. Influence lines for reactions, used to determine how the reactions it supports change with the position of a moving load. 2. Influence lines for internal forces, shear, bending moment, used to determine how internal forces like shear or bending moment change with the position of a moving load. 8.2. Influence lines for beams. The influence line for a beam is generally developed for a specific internal force, e.g., shear, bending moment, or reaction. The method used to determine the influence line will depend on the type of internal force and the boundary conditions of the beam, e.g., simply supported, cantilever, or continuous. 8.2.1. Influence line for reactions in a simply supported beam. Consider a simply supported beam of length LL, with a unit load moving across the span. Step 1. Apply a unit load. A unit load, usually 1 or 1 pound, is placed at various positions along the beam, and the reaction at one of the supports is calculated. Step 2. Calculate reactions. For each position of the unit load, calculate the reactions at the supports using equilibrium equations. Step 3. Plot the influence line. The reaction at the support is plotted as a function of the position of the unit load. Result: the influence line for the reaction at a given support is a straight line. The reaction at the left support is maximum when the load is at the right support, and vice versa. Example: influence line for reaction at left support of simply supported beam. For a simply supported beam with span L equals 10 milliliters equals 10 m, The influence line for the reaction at the left support, R1, is a straight line, ranging from 0 at the left end to 1 at the right end. The equation for this influence line is R1 equals L1 equals X, where is the distance from the left end where the unit load is placed, and LL is the length of the beam. 8.2.2 Influence line for shear force in a simply supported beam. To determine the influence line for shear force at a specific point on a simply supported beam. Step 1. Apply a unit load at various positions along the span of the beam. Step 2. Calculate the shear force at the point of interest for each position of the unit load. Step 3. Plot the shear force as a function of the position of the unit load. Result. The influence line for shear force in a simply supported beam is typically linear and will vary depending on the location of the point of interest. The shear force at the point of interest is highest when the load is nearest to that point. Example: influence line for shear at a point 4m from the left support. For a simply supported beam of length 10m, the influence line for shear at a point 4m from the left support can be computed by considering the shear force at that point as the unit load moves along the beam. The shear force will be positive when the load is to the left of the point and negative when the load is to the right of the point. 8.2.3 Influence line for bending moment in a simply supported beam. To determine the influence line for bending moment at a specific point on a simply supported beam. Step 1. Apply a unit load at various positions along the beam. Step 2. Calculate the bending moment at the point of interest for each position of the unit load. Step 3. Plot the bending moment as a function of the position of the unit load. Result. The influence line for bending moment at a point on a simply supported beam is typically triangular. The bending moment is maximum when the unit load is at the location of the point of interest. Example: influence line for bending moment at midspan of a simply supported beam. For a simply supported beam with a span of 10m, the influence line for the bending moment at midspan will be a triangular shape, peaking when the unit load is directly at midspan. 8.3 Influence lines for frames. Influence lines for frames are similar in concept to those for beams but are more complex due to the additional dimensions and internal forces in frames, which involve both bending and axial forces. 8.3.1 Influence line for reactions in a frame. The method for determining influence lines for reactions in a frame follows the same basic principles as for beams, but due to the additional degree of freedom at each joint, the calculations involve solving equilibrium equations for both horizontal and vertical forces, as well as moments. Step 1. Apply a unit load at various positions along the frame. Step 2. Calculate the reactions at the supports for each position of the unit load. Step 3. Plot the reaction as a function of the position of the load. 8.3.2 Influence line for shear forces in frames. For shear forces in frames, influence lines can be developed for each member of the frame. This process is similar to that for shear forces in beams but requires additional consideration of the frame's geometry. Step 1. Apply a unit load at various points along the frame. Step 2. Calculate the shear force in the frame member, or at a joint, for each position of the load. Step 3. Plot the shear force as a function of the position of the load. 8.3.3 Influence line for bending moments in frames. For a bending moment in a frame, the influence line is determined by applying a unit load at different positions along the frame, calculating the bending moment at the point of interest, and plotting the results. Step 1. Apply a unit load at various positions along the frame. Step 2. Calculate the bending moment at the point of interest in the frame for each position of the load. Step 3. Plot the bending moment as a function of the position of the load. Result. The shape of the influence line for bending moments in frames depends on the geometry of the frame and the location of the point of interest. 8.4. Practical example. Influence line for a frame. Consider a simple frame with a horizontal beam and vertical columns. We want to determine the influence line for the bending moment at a specific point on the beam. Step 1. Apply a unit load at various positions along the beam. Step 2. Calculate the bending moment at the point of interest, e.g., the midspin of the beam, for each position of the load. Step 3. Plot the bending moment as a function of the position of the unit load. The influence line will depend on the stiffness of the frame and the location of the support, and it may involve both linear and nonlinear segments. Determining influence lines for beams and frames is a crucial part of structural analysis, particularly when designing structures subject to moving loads. Influence lines help engineers determine the worst-case scenarios for internal forces, enabling more efficient and safer designs. While the method for determining influence lines involves applying a unit load at various positions and calculating the resulting internal forces, the complexity increases with the geometry of the structure, especially for frames. Understanding and plotting these influence lines allow engineers to optimize their designs for dynamic loads and ensure the structural safety and performance of various types of infrastructure. 8. Influence lines for moving loads. Application to moving load problems. Influence lines are an essential tool when dealing with moving loads in structural analysis. They help engineers evaluate how internal forces, such as shear, bending moment, or reaction forces, change as a load moves across a structure. This is especially important for structures like bridges, highways, and railways that are subjected to dynamic loads that vary in position over time. This section explains how influence lines are applied to typical moving load problems, helping engineers determine the worst-case internal forces and design structures that can safely withstand such loads. 8.1. Overview of moving load problems. Moving load problems involve the analysis of structures subjected to loads that change position over time. In these cases, the applied loads are not static but instead move across the structure, affecting internal forces in varying ways. Common examples of structures that experience moving loads include bridges, vehicle or train loads that move across the span, highways, trucks, cars, and other vehicles driving over the road, railroads, trains passing over railway tracks and overpasses, cranes and construction equipment, heavy machinery moving across a structure. In these situations, influence lines are used to determine how the internal forces vary as a moving load moves across the structure, allowing engineers to calculate the worst-case scenario for the forces at any point of interest. 8.2. Influence lines for moving loads in beam structures. Consider a simply supported beam subjected to a moving load, such as a truck or train. 8.2.1. Determining the internal force for a moving load. The key steps to applying influence lines for moving loads in beam structures are: 1. Calculate the influence line for the internal force. First, determine the influence line for the internal force, bending moment, shear force, or reaction, at the point of interest on the beam. This involves applying a unit load at different positions along the beam and calculating the resulting internal force, bending moment, shear, or reaction. 2. Identify the moving load. Define the magnitude and position of the moving load. For instance, in the case of a truck, you would have a load with a given weight moving across the beam. If the load is a train or a set of vehicles, the process is similar but may involve multiple point loads or a uniformly distributed load. 3. Determine the worst case position. The influence line tells you how the internal force, e.g., shear or bending moment, varies as the load moves. The worst case position is the location where the internal force is maximized. This is determined by observing the influence line for the load's position relative to the point of interest. 4. Calculate the internal force for the moving load. For each position of the moving load, use the influence line to determine the internal force at the point of interest. The internal force is the product of the load magnitude and the corresponding value on the influence line for that position. 5. Sum the forces. If the moving load consists of multiple point loads, e.g., a truck with multiple axles, calculate the internal forces for each axle position and sum them to get the total internal force. Example: moving load on a simply supported beam. Consider a simply supported beam of length L equals 12 milliliters equals 12 m and a moving truck load that consists of a uniform load W equals 10/m applied over a length equals 3m equals 3m. Step 1. Influence line for bending moment at midspin. First, determine the influence line for the bending moment at midspin. This is typically triangular for a simple beam. Step 2. Apply the moving load. Move the truck load, uniform load, across the beam. The position of the load relative to the point of interest, midspin, changes. Step 3. Find the worst case position. The worst case scenario occurs when the load is centered at midspin, as this is when the bending moment is maximized. Step 4. Calculate the bending moment. Multiply the magnitude of the truck load by the corresponding value on the influence line for each position of the load. Step 5. Sum the forces. For a distributed load, integrate the influence line over the length of the moving load to calculate the maximum bending moment. 8.3. Influence lines for moving loads on frames. Frames, like bridges or multi-span structures, are more complex than beams due to the presence of multiple members and the interaction between different internal forces, shear, bending, and axial forces. The process for applying influence lines to frames is similar to that for beams but involves additional complexity. 8.3.1. Steps for frames. 1. Calculate the influence line for the internal force. As with beams, determine the influence line for the internal force at the point of interest. For frames, this involves calculating how the internal forces, shear, moment, or axial force, vary at a particular joint or member as the moving load moves across the structure. 2. Apply the moving load. Define the magnitude and position of the moving load, which could consist of a single point load or a distributed load. For example, a truck load might consist of multiple point loads corresponding to the truck's axles. 3. Determine the worst case position. Identify the position of the load that maximizes the internal force at the location of interest in the frame. This can be determined by observing the influence line. 4. Calculate the internal force. For each position of the load, calculate the internal force using the influence line. This can be done by multiplying the load's magnitude by the corresponding value of the influence line. 5. Sum the effects of multiple loads. If the moving load consists of multiple point loads or is a distributed load, sum the internal forces for each load position. 8.4. Practical example. Influence line for moving loads on a bridge. Let's consider a simple bridge span, modeled as a simply supported beam, subjected to a truck load. We are interested in determining the maximum bending moment that occurs under the bridge as the truck moves across the span. Step 1. Influence line for bending moment at midspan. For a simply supported beam, the influence line for the bending moment at midspan is triangular. The maximum bending moment occurs when the load is placed at midspan. Step 2. Moving truck load. A truck with a load of 15 is moving across the span. As the truck moves, the bending moment changes at midspan. Step 3. Worst case load position. The maximum bending moment occurs when the truck is centered over the midspan of the beam. Step 4. Calculate maximum bending moment. Use the influence line to calculate the bending moment at midspan when the truck is at different positions along the span. The maximum bending moment will occur when the truck is at midspan. Step 5. Integrate the moving load. If the truck load is distributed, you will need to integrate the influence line over the length of the moving load to calculate the total internal force. 8.5. Application to other structural elements. In addition to beams and frames, influence lines can be applied to other types of structures subjected to moving loads, such as towers and cranes. Influence lines can be used to determine how forces change as the equipment moves along a structure. Cables and suspension bridges. Influence lines can help analyze how moving loads affect cable-stayed or suspension bridge systems. Railways. Influence lines are particularly useful in analyzing the forces in railway tracks and bridges as trains move across them. Influence lines for moving loads are invaluable tools for structural engineers when designing structures subjected to dynamic loads. By allowing engineers to visualize how internal forces, shear, bending moments, or reactions change as a load moves across a structure, influence lines enable the identification of worst-case scenarios. This analysis ensures that structures like bridges, highways, and railways can be designed to safely handle the forces imposed by moving loads, ensuring both safety and efficiency in their design and construction. (9) Dynamic structural analysis. Types of dynamic loads: earthquake, wind, etc. Dynamic structural analysis is essential for understanding how structures respond to time-varying loads, also known as dynamic loads. Unlike static loads, which remain constant or change slowly over time, dynamic loads are rapidly changing forces that can vary significantly during the course of their application. The most common types of dynamic loads include earthquake loads, wind loads, traffic loads, and impact loads. These loads can induce oscillations or vibrations in the structure, requiring specific methods of analysis to ensure that the structure can safely withstand them. In this section, we'll explore the main types of dynamic loads and their impact on structural systems. 9.1. Earthquake loads. Earthquake loads are forces generated by the seismic activity in the Earth's crust. When an earthquake occurs, seismic waves propagate through the ground, causing the ground to move, which in turn applies forces to any structures built on or near the affected area. Characteristics of earthquake loads. Time-varying nature. Earthquake forces change rapidly in time. The force experienced by a structure varies in magnitude and direction, and the frequency content of seismic waves can affect different structures in various ways. Base motion. The ground motion at the foundation or base of the structure can lead to large displacements, which are then transferred to the structure. Pulsating forces. Earthquakes produce forces that can act in all directions: horizontal, vertical, and rotational, but the most significant effects typically come from horizontal ground motion. Resonance risk. If the natural frequency of a structure matches the frequency of seismic waves, It can amplify the structural vibrations, causing potentially devastating effects. Key seismic loads. 1. Horizontal loads. These are the lateral forces generated by horizontal ground shaking, often the most critical component. 2. Vertical loads. These forces arise from vertical seismic movements, which are less common but can still have an impact, especially on tall structures or critical systems. 3. Moment loads. Earthquakes often induce torsional moments due to the uneven distribution of forces or irregularities in the building's shape. Earthquake analysis methods. Response spectrum analysis. A common approach to analyze earthquake forces, especially for linear structures. It uses a set of pre-calculated curves that represent the maximum response of structures at different frequencies. Time history analysis. In this method, the actual ground motion data, a time-varying acceleration, is used to compute the dynamic response of a structure over time. Modal analysis. Used to determine the natural frequencies and mode shapes of the structure, helping to predict how the structure will respond to different frequencies of seismic activity. 9.2. Wind loads. Wind loads result from the force exerted by the movement of air, typically caused by atmospheric pressure differences. These loads can significantly affect buildings, towers, bridges, and other tall structures. Characteristics of wind loads. Time varying. Wind speed and direction change with time, creating fluctuating forces on structures. This variation can be periodic or non-periodic, depending on factors like weather conditions and topography. Turbulence. Wind is often turbulent, with random fluctuations in speed and direction, which can cause dynamic effects on structures. Pressure distribution. The wind pressure is not uniform across the surface of a structure. The pressure distribution depends on the shape and height of the structure, as well as the wind speed. Types of wind loads. 1. Steady wind loads. These occur when wind blows at a constant velocity. For example, a structure subjected to a constant wind speed will experience a continuous force. 2. Fluctuating wind loads. Wind speed fluctuates due to turbulence, creating varying pressures on the structure. This is a major cause of dynamic vibrations in tall buildings or bridges. 3. Dynamic wind loads. Caused by changes in wind velocity and direction. These loads lead to dynamic responses in structures such as sway and oscillations. Wind analysis methods. Building aerodynamics. Modern wind engineering uses wind tunnel testing and computational fluid dynamics, CFD, simulations to study how buildings interact with wind. Wind load calculation. Codes such as ASCE 7 or Eurocode 1 provide guidelines on calculating wind loads based on factors such as building height, shape, location, and exposure to wind. Dynamic wind response. Wind-induced vibrations can be analyzed using dynamic analysis methods, including gust factor and resonance considerations to ensure that the structure does not undergo excessive oscillations. 9.3. Traffic loads. Vehicle loads. Traffic loads, such as those caused by vehicles passing over bridges, highways, and pavements, are another form of dynamic load that affects the design of road structures. Characteristics of traffic loads. Time varying. The position, speed, and magnitude of the load change as vehicles move along the roadway. Traffic loads can vary from a single point load, a single vehicle, to a uniformly distributed load, multiple vehicles, or a traffic jam. Impact forces. The wheels of vehicles create dynamic loads that cause vibrations and transient forces as they impact the structure. Live load variation. The load distribution and magnitude change depending on vehicle types, such as cars, trucks, or buses, and the number of vehicles on the structure at any given time. Key traffic load types. 1. Point loads represent individual vehicles or trucks passing over a bridge. 2. Moving load. As vehicles move across a structure, their position and load distribution change. Influence lines are often used to model this type of dynamic load. 3. Impact loads. Traffic impact loads occur when a vehicle moves over a bump, pothole, or sudden change in the structure, causing additional dynamic forces. Traffic load analysis methods. Vehicle load models. Engineers use standard vehicle models, such as the S20 load for highway bridges, to simulate the dynamic effects of traffic. Dynamic response. The dynamic amplification factor is often used to account for the increased force caused by the impact of vehicle wheels on the structure. Moving load analysis. Similar to wind and seismic analysis, moving vehicle loads require special analysis to determine the maximum forces at critical locations on the structure as the load moves. 9.4. Impact loads. Impact loads are sudden and large forces that are applied to a structure over a very short period of time. These loads can result from events like collisions, falls, or explosions. Characteristics of impact loads. Short duration. Impact loads are typically very short in duration but have a large magnitude. The force is concentrated over a small area, causing rapid and intense deformations. High velocity. Impact loads are often associated with high velocity events, such as a moving vehicle crashing into a structure. Local effects. Impact loads can cause localized damage to structural elements, such as dents, fractures, or stress concentrations. Impact load analysis methods. Dynamic amplification. The structural response to impact loads is often amplified due to the high velocity and short duration of the applied load. Engineers must account for this amplification in their analysis. Time history analysis. For complex impact scenarios, like explosions or machinery failures, time history analysis is often used to model the exact response of the structure over time. 9.5. Other dynamic loads. In addition to earthquakes, wind, traffic, and impact loads, there are other dynamic forces that can affect structures. Machinery vibrations. Vibrations from industrial machinery, elevators, or HVAC systems can cause dynamic loading on surrounding structures. Marine loads. Offshore structures, such as oil rigs, are subjected to dynamic forces from waves, tides, and water currents. Thermal loads. Changes in temperature can cause thermal expansion and contraction, generating internal forces that vary with time. Dynamic loads play a crucial role in the analysis and design of structures, particularly in regions subject to significant seismic activity or areas exposed to strong winds. Understanding and accurately modeling these dynamic loads is essential to ensure the safety and stability of structures under real-world conditions. Engineers use various methods, including time history analysis, response spectrum analysis, and modal analysis, to assess how structures will behave under the influence of dynamic loads like earthquakes, wind, traffic, and impact forces. Properly accounting for these forces helps to mitigate risks and ensure that structures can withstand the forces they are likely to encounter over their service life. 9. Dynamic structural analysis. Free vibration analysis of structures. Free vibration analysis is a critical component of dynamic structural analysis. It involves studying how a structure responds to initial disturbances without the influence of external forces after the disturbance is applied. In free vibration, a structure vibrates naturally at specific frequencies determined by its material properties, shape, and boundary conditions. The analysis of these vibrations helps engineers understand how a structure might behave in response to events like earthquakes, wind, or machinery operation. In this section, we'll explore the key principles and methods for performing free vibration analysis of structures. 9.1. What is free vibration? Free vibration occurs when a structure is displaced from its equilibrium position and then allowed to vibrate without any ongoing external force being applied. After the initial disturbance, the structure will oscillate at its natural frequencies and mode shapes. For example, when a building or bridge shakes due to a wind gust, earthquake, or even an initial impact, the structure will oscillate in a specific pattern, known as the mode shape, at specific frequencies known as natural frequencies. Key parameters in free vibration. 1. Natural frequency, the frequency at which a structure naturally tends to vibrate when disturbed. It depends on the mass and stiffness of the structure. 2. Mode shape, the shape or pattern of deformation that a structure undergoes as it vibrates at its natural frequency. Each mode shape corresponds to a specific natural frequency. 3. Damping. In real-world systems, damping, the dissipation of vibrational energy, gradually reduces the amplitude of vibrations over time. However, for free vibration analysis, damping is typically neglected, and the system is considered to oscillate indefinitely without losing energy. 9.2. Governing equations for free vibration. The free vibration of a structure can be described by a set of second-order differential equations. These equations represent the balance between the inertial forces, due to mass, and the restoring forces, due to stiffness. For a simple system, such as a mass spring system, the equation of motion is given by 2x, t, 2 plus t, equals 0, 2d 2x, t, plus t, equals 0, where is the mass of the system, is the stiffness of the system, x, t, is the displacement of the mass at time. For more complex systems, such as structures with many degrees of freedom, e.g., buildings, bridges, or frames, the equations can be written in matrix form as m x t plus k x t equals 0, m x t plus k x t equals 0, where m is the mass matrix, representing the distribution of mass throughout the structure. K is the stiffness matrix, representing the distribution of stiffness. X t is the acceleration, second derivative of displacement. X t is the displacement vector. These equations describe how the structure deforms and oscillates over time after being disturbed. 9.3. Solution to the free vibration problem. To solve for the natural frequencies and mode shapes of a structure, the governing equations must be solved for the system's characteristic equation. This is done by assuming a solution of the form x t equals xsin t plus x t equals sin t plus, where 20 is the amplitude vector, mode shape is the angular frequency, related to the natural frequency by equals 2 is the phase angle, which is often set to 0 for simplicity. Substituting this assumed solution into the equations of motion leads to the eigenvalue problem. K x equals m x k x equals M, X. This is a generalized eigenvalue problem, where are the eigenvalues, which represent the squared natural frequencies. 20 are the eigenvectors, which represent the mode shapes of the structure. Steps in free vibration analysis. 1. Formulate the mass and stiffness matrices. For a structure, we first need to derive the mass and stiffness matrices, which represent how mass and stiffness are distributed throughout the structure. These are generally done through lumped mass models for simple structures or more detailed formulations for complex systems. 2. Solve the eigenvalue problem. Once the mass and stiffness matrices are available, the eigenvalue problem is solved to find the natural frequencies and corresponding mode shapes, eigenvectors 20. 3. Interpret the results. The natural frequencies and mode shapes give insight into how the structure will vibrate when disturbed. For example, if the natural frequency of the structure coincides with an external force, like the frequency of seismic waves or wind gusts, resonance can occur, leading to large amplitude oscillations that may damage the structure. 9.4. Modal analysis. Modal analysis is a technique used to determine the natural frequencies and mode shapes of a structure. It breaks down complex vibrations into simpler components, modes, making it easier to analyze how each mode contributes to the overall dynamic response. Steps in modal analysis. 1. Model the structure. Divide the structure into simpler components, finite elements, each with its own mass and stiffness properties. 2. Solve for modes. Use the mass and stiffness matrices to solve the eigenvalue problem and obtain the natural frequencies and mode shapes. 3. Interpret the modes. Each mode shape represents a unique way in which the structure deforms during vibration. The first mode corresponds to the lowest natural frequency and typically involves the entire structure vibrating in a simple pattern, e.g., the entire building swaying. Higher modes correspond to higher frequencies and often involve more complex deformation patterns. 9.5. Importance of free vibration analysis in structural design. Free vibration analysis is important in structural design for the following reasons. 1. Resonance prevention. Resonance occurs when the natural frequency of a structure coincides with the frequency of an applied load. This can lead to excessive vibrations and structural failure. By identifying natural frequencies, engineers can design structures to avoid resonance with common dynamic forces, e.g., wind, traffic, machinery. 2. Seismic design. Structures in earthquake-prone areas are especially vulnerable to resonance with seismic waves. Free vibration analysis helps determine the natural frequencies of buildings and bridges, which can then be used to ensure that the structure does not vibrate excessively during an earthquake. 3. Wind-induced oscillations. Tall buildings and bridges are susceptible to wind-induced vibrations. Free vibration analysis helps predict these vibrations and ensures that the structure has adequate damping or stiffness to mitigate them. 4. Reducing vibrations from machinery. In industrial settings, machines and equipment can introduce vibrations that may negatively affect the structural integrity of nearby buildings or equipment. Free vibration analysis helps identify potential vibration problems and suggests design modifications. 5. Optimizing structural performance. Knowing the natural frequencies and mode shapes allows engineers to optimize the design of the structure to improve its performance under dynamic loading, while minimizing the risk of failure due to excessive vibrations. 9.6. Example. Free vibration of a simple beam. Consider a simply supported beam with a uniform mass distribution. The equation for the natural frequencies of the beam is derived from the governing differential equation for vibration. For a beam, the natural frequencies are given by equals n22 il4 equals l4 n22a, where is the mode number 1, 2, 3. E is the Young's modulus of the material. 2 is the second moment of area, or moment of inertia. LL is the length of the beam, is the density of the material. EA is the cross-sectional area. This formula gives the natural frequencies of a simply supported beam, and the corresponding mode shapes describe the different patterns of deflection as the beam vibrates. Free vibration analysis is a fundamental part of dynamic structural analysis, providing insight into the natural frequencies and mode shapes of a structure. By understanding how structures vibrate naturally, engineers can design buildings, bridges, and other infrastructure to avoid resonance with dynamic loads such as wind, earthquakes, or machinery-induced vibrations. This analysis helps ensure that structures remain stable and safe under real-world conditions. 9. Dynamic structural analysis. Response spectrum and time history analysis. In dynamic structural analysis, response spectrum and time history analysis are two critical methods used to analyze how structures respond to dynamic loads, such as earthquakes, wind, and other transient forces. Both methods are employed to understand the displacement, stress, and strain that a structure experiences when subjected to dynamic forces, but they differ in their approach, application, and level of detail. In this section, we'll explain each method, compare their advantages and disadvantages, and explore their applications in structural analysis. 9.1. Response spectrum analysis. Response spectrum analysis, RSA, is a method used to determine the peak response, such as displacement, velocity, or acceleration, of a structure subjected to a dynamic load, without solving the equations of motion for every time step. What is a response spectrum? A response spectrum is a plot that shows the maximum response, typically displacement or acceleration, of a single degree of freedom system to a particular input excitation, like ground motion during an earthquake, at different frequencies. In simple terms, it is a graph of the maximum peak response of structures of varying natural frequencies, or modes, when subjected to a specific dynamic load. How does response spectrum analysis work? Step 1. Modal analysis. First, the structure is analyzed using modal analysis to find its natural frequencies and mode shapes, as discussed in free vibration analysis. This step breaks down the complex structure into its vibrational modes. Step 2. Determine response spectrum. The response spectrum for the given dynamic load, such as an earthquake or wind load, is either obtained from experimental data, like ground motion records for seismic events, or computed from known excitation characteristics. Step 3. Modal superposition. After the response spectrum is obtained, the individual responses for each mode of the structure are calculated. These responses are typically linearly superimposed to determine the total response of the structure. This approach assumes that the modes do not significantly interact with each other, a simplifying assumption that holds true for most practical cases. Key features of response spectrum analysis. Time-independent. RSA is a time-independent analysis method, meaning it doesn't track the dynamic response over time. Instead, it computes the peak response of each mode, assuming that each mode reacts independently to the excitation. Simplification. RSA is a simplification that avoids solving the full equations of motion, which would require detailed time history analysis. This makes it computationally less expensive and quicker to perform. Modal superposition. The total response is the sum of the peak responses of the individual modes. A modal combination rule, such as the absolute sum or complete quadratic combination, is used to combine these peak responses to get the overall structure response. Applications of response spectrum analysis. Seismic analysis. RSA is widely used in seismic engineering to evaluate how structures, such as buildings, bridges, and dams, respond to earthquakes. The seismic excitation is typically represented as a response spectrum derived from actual ground motion data or from a design spectrum based on seismic hazard analysis. Wind load analysis. RSA can be used for analyzing structures subjected to dynamic wind forces, especially for tall buildings and towers. Efficiency. RSA is often used for preliminary design stages or when a quick assessment is needed without requiring a full time history analysis. Limitations of response spectrum analysis. Single degree of freedom, STOF. Assumption. RSA assumes that each mode behaves as a single degree of freedom, STOF, system, which may not always be accurate, particularly for complex structures with closely spaced natural frequencies. Mode independence. The method assumes that the modes are independent and that there is no significant interaction between them, which may not hold true in structures with closely spaced natural frequencies. 9.2. Time history analysis. Time history analysis, is a more detailed and accurate method of dynamic analysis that involves solving the equations of motion over time to determine how a structure responds to time-varying loads. What is time history analysis? Time history analysis involves the application of a time-varying load, such as an earthquake ground motion or wind gusts, to a structure and solving the resulting equations of motion to compute the structure's response at every point in time. The time history is typically represented as a series of displacement, velocity, or acceleration data over a period, and the structure's dynamic response is obtained at each time step. How does time history analysis work? Step 1. Input dynamic load. The dynamic load, e.g., seismic ground motion, wind load, is represented as a time history. In seismic analysis, this is usually a set of acceleration time histories recorded during an earthquake. Step 2. Solve equations of motion. The governing differential equations of motion for the structure are solved numerically, step by step, to compute the displacements, velocities, and accelerations of the structure at each time step. Step 3. Evaluate response. The response of the structure is computed over the entire duration of the load application. This can be plotted over time to visualize how the structure's displacement, velocity, or acceleration evolves. Key features of time history analysis. Time-dependent. Unlike RSA, that provides a time-dependent response of the structure, which means it tracks the entire dynamic behavior of the structure throughout the loading event. Detailed information. That provides more detailed information about how the structure responds over time, which is essential when studying complex events such as earthquakes or impacts. Nonlinear analysis. That can be extended to nonlinear structural analysis, where the material properties or the geometry of the structure change during the loading, allowing for more realistic simulations of structural behavior under extreme loads. Applications of time history analysis. Seismic design. Time history analysis is commonly used in earthquake engineering to study the response of structures under specific earthquake ground motions. This method is particularly useful when dealing with complex structures or nonlinear behaviors, such as soil-structure interaction, dynamic amplification, and resonance. Wind-induced vibrations. That is also used in analyzing structures subject to dynamic wind loads, particularly for tall buildings and bridges, where wind forces vary rapidly over time. Impact and collision analysis. Time history analysis can model impacts, vehicle collisions, or other transient events that produce short-duration, high-intensity loads. Advantages of time history analysis. Accuracy. That is more accurate than RSA because it solves the exact equations of motion over time, capturing the full time-dependent response of the structure. Detailed results. It provides detailed information about the structure's response, including maximum displacements, velocities, accelerations, and forces over time. Nonlinear capability. Time history analysis can incorporate nonlinear behavior, such as material yielding, geometric nonlinearity, e.g., large deformations, and damping, which are essential for accurately modeling extreme events like earthquakes and large winds. Limitations of time history analysis. Computationally intensive. That requires solving differential equations at many time steps, which can be computationally expensive, particularly for large structures or long-duration events. Requires detailed input data. That requires accurate time history data, e.g., ground motion records, or detailed load history data, which may not always be available. Complexity. Due to the need for time-dependent load data and numerical methods, that is more complex to set up and interpret compared to response spectrum analysis. 9.3. Comparing response spectrum analysis and time history analysis. Characteristic. Response spectrum analysis, RSA. Time history analysis. The approach. Frequency-based, peak response of modes. Time domain. Full dynamic response over time. Computation. Less computationally intensive. More computationally intensive. Accuracy. Approximate. Suitable for linear systems. More accurate. Accounts for full time-dependent response, including nonlinear effects. Mode interaction. Assumes modes are independent. Accounts for mode interaction and full dynamic behavior. Application. Quick evaluation. Seismic design. Wind load analysis. Detailed analysis. Seismic and wind analysis. Impact events. Limitations. Assumes linear behavior. Doesn't track time response. Requires detailed input data. Computationally expensive. Both response spectrum analysis, RSA, and time history analysis, THE, are essential tools for dynamic structural analysis. RSA is a simplified, frequency domain method that is computationally efficient and is typically used for preliminary design and analysis, especially for seismic and wind loads. On the other hand, time history analysis provides a more detailed, time domain response and is ideal for understanding complex structural behavior during events like earthquakes, windstorms, or impacts. The choice between RSA and THE depends on the nature of the dynamic loading, the complexity of the structure, the level of detail required, and the available computational resources. Engineers often use both methods at different stages of design, using RSA for quick evaluations and THE for more detailed, high-fidelity analyses. 9. Dynamic structural analysis. Damping and energy dissipation. In dynamic structural analysis, damping refers to the process by which a structure dissipates the energy imparted to it by dynamic loads, such as earthquakes, wind forces, or any time-varying excitation. Energy dissipation plays a crucial role in reducing the amplitude of oscillations, controlling vibrations, and ensuring the structural safety and comfort of the occupants. Understanding how damping works in a structure and how energy is dissipated is critical for designing systems that can withstand dynamic loads without excessive motion or failure. 9.1. What is damping? Damping is the mechanism by which the energy of a vibrating structure is dissipated over time, typically in the form of heat or other forms of energy. In simple terms, damping reduces the motion, displacement, velocity, or acceleration of a vibrating system by converting some of the system's mechanical energy into other forms of energy, such as heat. Types of damping. 1. Viscous damping. In this type of damping, the force resisting motion is proportional to the velocity of the vibrating object. The damping force is typically expressed as F equals CV Fd equals CV, where F is the damping force, V is the damping coefficient, and V is the velocity. 2. Coulomb. Dry damping. This type of damping is caused by friction between two surfaces. The damping force is constant and independent of the velocity of the vibrating object, typically modeled as a constant resistive force opposite to the direction of motion. 3. Hysteretic damping. In hysteretic damping, the energy is dissipated through internal friction in the material or structure. This type of damping is commonly observed in materials undergoing plastic deformation, e.g., during large-scale cyclic loading like earthquakes, or in structures with nonlinear behaviors. 4. Structural damping. This involves energy dissipation mechanisms intrinsic to the structural elements, such as the internal damping of beams, columns, and joints, and is generally represented by the sum of various damping effects. 9.2. Damping models in structural analysis. In dynamic structural analysis, damping is typically modeled in one of the following ways. Viscous damping model. Equation. The viscous damping force is often modeled as V equals Cx Fd equals Cx, where V is the damping force, V is the damping coefficient, a constant that depends on the material and structure. Xx is the velocity of the structure. Damping matrix. In matrix form, the damping force is often represented as V equals CV Fd equals CV, where F is the vector of damping forces, V is the damping matrix, and V is the vector of velocities. Rayleigh damping. Proportional damping. Rayleigh damping assumes that the damping matrix Cc is a linear combination of the mass matrix and the stiffness matrix Kk. C equals m plus k, C equals m plus k, where Cc is the damping matrix, and are constants that control the relative contribution of mass and stiffness to the damping behavior. Is the mass matrix, and Kk is the stiffness matrix. Application. Rayleigh damping is widely used in structural analysis for simplifying the modeling of damping in large systems and for practical computational purposes. 9.3. Energy dissipation in dynamic systems. Energy dissipation refers to the conversion of mechanical energy into other forms of energy, such as heat, sound, or light, within the system. In a structural system, when subjected to dynamic loading, e.g., an earthquake or wind gust, the structure absorbs and then dissipates the energy in several ways, depending on its materials and damping properties. Energy dissipation mechanisms. 1. Internal friction. Material damping. In materials, energy dissipation occurs as internal friction between particles or molecules, converting mechanical energy into heat. This is particularly evident in materials undergoing plastic deformation. 2. Frictional damping. For structures with joints, connections, or sliding parts, energy dissipation can occur through frictional resistance. This type of damping is nonlinear and depends on the displacement and velocity of the sliding surfaces. 3. Viscous damping. Fluid-based systems. Damping can also occur in systems where a fluid, like oil or gas, is involved, such as in dampers used in structural systems, e.g., shock absorbers. Energy is dissipated as the fluid resists the movement of a piston or other components. 4. Hysteretic damping. Nonlinear systems. In some structures, particularly those that undergo plastic deformation, like steel or reinforced concrete structures, energy is dissipated through the cyclic deformation of materials, leading to hysteresis loops in stress-strain curves. 9.4. Damping in structural design. In practical structural design, damping plays an essential role in controlling vibrations, protecting the structure from excessive displacements, and improving its overall performance under dynamic loads. Damping systems are often incorporated into the design to reduce vibrations and improve the serviceability of structures. Types of damping systems. 1. Viscoelastic dampers. These dampers absorb energy through the deformation of viscoelastic materials. They are often used in tall buildings, bridges, and other structures subject to seismic or wind forces. 2. Tuned mass dampers, TMD. A tuned mass damper consists of a large mass mounted on a spring and damper system. It is typically used in high-rise buildings or towers to reduce wind-induced vibrations or sway. 3. Friction dampers. These are used in structural joints or connections, where friction between surfaces dissipates energy. They are commonly used in bridges and buildings to reduce vibrations. 4. Shock absorbers. Shock absorbers, commonly used in vehicles, can also be used in structural systems to absorb large dynamic forces, particularly in the case of impacts or earthquakes. 5. Base isolation systems. These systems decouple a building or structure from ground motion during an earthquake, reducing the amount of energy transferred to the structure. These systems include flexible bearings and dampers. 9.5. Importance of damping in seismic design. Damping plays a crucial role in seismic design, where controlling the dynamic response of a building to an earthquake is critical for its safety. Structures with higher damping will have lower peak displacements and forces during an earthquake. Seismic damping techniques. Base isolation. In regions with high seismic activity, base isolation systems reduce the energy transferred from the ground to the structure. By isolating the building from the ground motion, these systems reduce the peak displacement and accelerations. Damping in steel and concrete structures. Steel and reinforced concrete buildings often incorporate dampers or braces that dissipate energy during seismic events, preventing excessive movements and damage. Vibration control for tall buildings. Tall buildings are more susceptible to sway during earthquakes. Using damping systems such as tuned mass dampers can significantly reduce lateral movements and prevent structural damage. 9.6. Energy dissipation and structural performance. In structures subjected to dynamic loading, particularly in seismic or wind events, energy dissipation contributes to the overall structural performance by 1. Reducing the amplitude of vibrations. Damping reduces the amplitude of vibrations and the total displacement of the structure, minimizing the risk of structural failure. 2. Improving safety. By reducing excessive vibrations, damping enhances the comfort and safety of building occupants, particularly in tall buildings or bridges. 3. Mitigating fatigue and damage. Damping helps in preventing the accumulation of stress and strain cycles in materials, thus reducing the risk of fatigue and material failure over time. 4. Increasing serviceability. Damping ensures that the structure remains functional and comfortable for occupants, even in the presence of dynamic loads. Damping and energy dissipation are fundamental aspects of dynamic structural analysis. These mechanisms are crucial for controlling vibrations and ensuring the safety and performance of structures under dynamic loads such as earthquakes, wind, or impacts. Understanding the types of damping and energy dissipation, as well as the methods to incorporate them into designs, is vital for structural engineers working in fields like seismic design, vibration control, and dynamic load management. By effectively incorporating damping systems into the design of buildings, bridges, and other structures, engineers can significantly enhance their resilience to dynamic loads and improve their overall performance. 10. Advanced topics in structural analysis. Nonlinear structural analysis. Nonlinear structural analysis is a critical aspect of advanced structural engineering that deals with the behavior of structures under loading conditions where the assumptions of linearity no longer hold true. While linear analysis assumes that the relationship between forces and displacements is proportional, i.e., Hooke's law, nonlinear analysis accounts for complex behaviors like material plasticity, large deformations, and geometric nonlinearities, which are crucial for accurately predicting the performance of structures under extreme conditions. Nonlinear behavior can arise from several sources, including material nonlinearity, when materials experience stress-strain relationships that are not linear, such as unyielding, cracking, or buckling. Geometric nonlinearity, when large displacements or rotations occur, causing significant changes in the geometry of the structure, which affects its stiffness and overall response. Boundary condition nonlinearity, when constraints or boundary conditions change due to deformation, such as nonlinear contact or sliding. Nonlinear structural analysis allows engineers to predict the behavior of structures more accurately under extreme loading conditions, which is especially important in the design of structures subjected to seismic, wind, or impact loads. 10.1. Types of nonlinearities in structural analysis. 1. Material nonlinearity. Elastic nonlinearity occurs when the material's stress-strain relationship deviates from the linear elastic model, typically seen in materials with a large range of elastic deformations before yielding. Plasticity. This is the most common form of material nonlinearity, where a material undergoes permanent deformation after exceeding its yield point. The analysis involves capturing the material's post-yield behavior, e.g., strain hardening or softening. Viscoelasticity involves both elastic and time-dependent viscous behavior. It is important in materials like rubber or polymer-based composites, where the structure exhibits both elastic and time-dependent responses. Fracture and damage. Materials may experience cracking or damage that alters their stiffness. Damage models help simulate the propagation of cracks and the degradation of material properties. 2. Geometric nonlinearity. Large deformations. When displacements are large enough that the structure's geometry changes significantly, the linear assumption of small deformations no longer holds. The structure's stiffness matrix changes with deformation, and the equilibrium equations become nonlinear. P-delta effects. These effects occur in structures under vertical loads, such as gravity, where large lateral displacements cause an additional moment due to the offset between the applied load and the deformed geometry. This is critical for tall buildings and structures with slender shapes. Instabilities. Geometric nonlinearities also play a role in buckling, snapping, or instability phenomena, where small changes in loading can cause a sudden and dramatic change in structure behavior. 3. Contact and boundary condition nonlinearity. Nonlinear contact. This occurs when parts of the structure come into contact or move apart during loading. For example, joints, supports, and interfaces between materials can experience nonlinear behavior. Frictional effects. Frictional forces between surfaces can introduce nonlinear behavior, especially when sliding or separation occurs. Friction models are often included in nonlinear analysis to simulate this behavior. 10.2. Techniques for nonlinear structural analysis. Nonlinear structural analysis involves more complex numerical techniques compared to linear analysis. The key approaches include 1. Incremental iterative solution methods. Nonlinear problems are typically solved iteratively because the relationship between forces and displacements is not straightforward. The process generally involves solving the nonlinear system incrementally, applying a series of small load steps and updating the structural response at each iteration. Newton-Raphson method. This is the most common iterative method for solving nonlinear equations. In this method, an initial guess for the solution is improved in successive steps by linearizing the system around the current solution and solving for the next iteration. Modified Newton-Raphson method. An extension of the standard Newton-Raphson method that modifies the tangent stiffness matrix to improve convergence. 2. Load step analysis. Static load increment. The load is applied in increments, and after each increment, the structure's response is updated. This is done until the final load is reached, or until the structure undergoes significant nonlinear behavior. Dynamic time history analysis. When the load changes over time, like in seismic or impact loading, dynamic analysis methods such as time history analysis are used. Nonlinear time history analysis considers both the transient nature of the loading and the nonlinear behavior of the structure. 3. Nonlinear finite element methods, FEM. Nonlinear FEM is widely used to model complex structures subjected to nonlinear behavior. The finite element method, FEM, is modified to account for material, geometric, and boundary nonlinearities. The nonlinear stiffness matrix changes at each step of the analysis, and the solution procedure requires updating the matrix as the structure deforms. 10.3. Applications of nonlinear structural analysis. Nonlinear structural analysis is crucial in various real-world applications, particularly where structures are subjected to extreme or complex loading conditions. Some notable applications include 1. Seismic analysis. Nonlinear analysis is critical for accurately predicting the behavior of buildings and bridges during an earthquake. Structures such as high-rise buildings and dams may undergo significant inelastic deformations, and capturing this behavior ensures proper design to prevent failure. Pushover analysis. This method involves applying a monotonically increasing lateral load to a structure until it reaches a predefined displacement, which helps engineers assess the structure's capacity to resist seismic forces. 2. Buckling and instabilities. Buckling analysis in columns, frames, or shells requires nonlinear analysis, as the structure can undergo large deformations before buckling occurs. Nonlinear models help predict the critical load at which buckling happens and simulate the post-buckling behavior. Snap-through behavior in structures like domes or arches, where the structure may undergo a sudden and large deformation, is also analyzed using nonlinear techniques. 3. Post-yield and plastic behavior. Nonlinear analysis is necessary for predicting the behavior of materials and structures after they reach their yield points, such as plastic hinges in beams or plastic zones in reinforced concrete. Plastic collapse. Understanding how a structure behaves after yielding, including localized plasticity and redistribution of internal forces, helps in evaluating the safety and serviceability of structures beyond the elastic range. 4. Impact and blast loading. Structures subjected to dynamic, high-intensity forces such as explosions, impacts, or vehicle collisions require nonlinear analysis to predict large deformations, material failure, and dynamic responses. These events often involve complex material behaviors and large displacements that cannot be captured using linear methods. 5. Large-scale deformations in soft materials. Nonlinear analysis is essential for modeling materials and structures that undergo significant deformations, such as rubber, polymer composites, or geotechnical structures, e.g., soil structure interaction during earthquakes. 10.4. Challenges in nonlinear structural analysis. 1. Computational complexity. Nonlinear analysis requires more computational power and time due to the iterative methods and the need to update the system's stiffness matrix after each load increment. For large-scale structures, nonlinear analysis can become computationally expensive, requiring high-performance computing systems or specialized software. 2. Convergence issues. The iterative solution methods may encounter convergence difficulties, especially in highly nonlinear systems with significant geometric or material nonlinearities. Ensuring that the solution converges to a physically realistic result requires careful selection of solution techniques and convergence criteria. 3. Modeling challenges. Accurate modeling of nonlinear behavior requires detailed material models, e.g., for concrete, steel, or composites, and geometric representations of the structure. Failure to correctly model these aspects can lead to inaccurate results. Nonlinearities like friction, contact, or damping must also be carefully modeled to reflect real-world behavior accurately. Nonlinear structural analysis is an essential tool for predicting the behavior of structures under extreme loading conditions. By incorporating material, geometric, and boundary nonlinearities, engineers can design more resilient structures capable of withstanding large deformations, seismic events, and other challenging conditions. Although nonlinear analysis introduces significant complexity, it provides a deeper understanding of a structure's true behavior, which is crucial for ensuring safety and reliability in modern engineering applications. As computational power continues to improve and more sophisticated methods emerge, nonlinear structural analysis will become increasingly accessible and integral to the design of safe and efficient structures. 10. Advanced topics in structural analysis. Buckling analysis of structures. Buckling refers to the sudden failure or instability of a structure when subjected to axial compressive loads. It is a critical phenomenon that occurs in slender structures, such as columns, beams, and shelves, when a load exceeds a certain threshold. At this point, the structure experiences a rapid, lateral deformation, potentially leading to catastrophic failure. Buckling analysis is essential to predict the load at which a structure becomes unstable and to design structures to avoid such failure modes. In buckling analysis, the primary goal is to determine the buckling load, the critical load at which a structure becomes unstable, and to understand the nature of the deformations that occur as the structure buckles. 10.1. Types of buckling. 1. Elastic buckling. Elastic buckling occurs when a structure, particularly a slender member, is subjected to axial compressive forces. If the compressive force exceeds a critical value, the structure will deform laterally in an elastic manner. Euler's buckling formula is often used for elastic buckling analysis in straight columns. For a pin-ended column, The critical buckling load was given by P equals L22A, where P is the critical buckling load. E is the modulus of elasticity. 2 is the second moment of area moment of inertia. LL is the length of the column. This formula applies to long, slender columns where the material remains elastic during buckling. 2. Inelastic buckling. Inelastic buckling occurs when the structure has already undergone some plastic deformation before buckling, often in materials like steel or concrete. The structure may undergo plastic yielding before buckling and could continue to deform after reaching the critical load, unlike elastic buckling where the deformation is limited. 3. Lateral torsional buckling. This type of buckling occurs in structural elements like beams or shafts that are subjected to bending. If the beam has insufficient lateral support, it may buckle laterally, causing both bending and torsion to occur simultaneously. This typically occurs in unbraced beams. The stability of the structure is influenced by its stiffness, the geometry of the cross-section, and the length of the beam. 4. Local buckling. Local buckling occurs when parts of the structure, typically thin-walled members such as plates, stiffeners, or shelves, buckle locally under compression before the whole structure reaches the critical buckling load. In this case, the local deformation leads to instability in the member, even though the overall structure might remain stable. An example is the local buckling of plates in a steel column under compressive load, where the plate itself buckles, leading to a decrease in the load-bearing capacity of the section. 5. Torsional buckling. This type of buckling occurs when a structural member undergoes a twisting motion, and it is commonly seen in thin-walled sections under compression. When a structure is subjected to compressive forces, it may twist about its longitudinal axis, leading to torsional instability. 10.2. Factors affecting buckling. Several factors influence the buckling behavior of structures, including 1. Geometry of the structure. The length of a column or structural element has a direct relationship with buckling. Slender structures are more likely to buckle under compressive loads. The cross-sectional shape and size also influence buckling behavior. For instance, structures with circular cross-sections or I-beams are generally more resistant to buckling than solid rectangular sections. 2. End conditions. The type of support or boundary conditions at the ends of the structure, e.g., pinned, fixed, or free, plays a critical role in determining the buckling load. Pin-ended columns allow rotation and displacement in the direction of the load. Fixed-ended columns prevent both rotation and displacement, leading to higher buckling resistance. Fixed pinned or free columns offer intermediate resistance, depending on how the load is applied. 3. Material properties. The modulus of elasticity, E, and the yield strength of the material significantly influence buckling behavior. Materials with higher stiffness, higher E, can withstand higher buckling loads. Material plasticity plays a role in inelastic buckling, where the material can undergo significant plastic deformation before the structure reaches its ultimate buckling capacity. 4. Axial load magnitude. The magnitude of the axial compressive force is the key factor that influences the buckling load. As the axial force increases, the structure eventually reaches a critical point, where the load causes it to buckle. 5. Slenderness ratio. The slenderness ratio is a dimensionless quantity that compares the effective length of a column to its radius of gyration. It is defined as equals L/A equals I/LL, where LL is the length of the column. 2 is the second moment of area moment of inertia. A is the cross-sectional area. Is the radius of gyration. A higher slenderness ratio indicates a more slender structure, which is more susceptible to buckling. A lower slenderness ratio means the structure is more resistant to buckling. 10.3. Buckling analysis methods. Various methods are used to analyze buckling behavior in structures. 1. Analytical methods. For simple cases like columns or beams with uniform cross-sections and ideal boundary conditions, Euler's critical buckling load formula provides an exact solution. For more complex problems, such as structures with varying cross-sections, more advanced analytical methods, such as the energy method or Rayleigh's principle, can be applied. 2. Finite element method, FEM. The finite element method is widely used for complex buckling problems involving irregular shapes, varying material properties, and complex boundary conditions. FEM can model the structure's response under loading and determine the eigenvalue corresponding to the buckling load. Buckling analysis in FEM involves solving an eigenvalue problem where the critical buckling load corresponds to the first eigenvalue, and the buckling mode shapes represent the structure's deformation under the applied load. 3. Pushover analysis. In the case of nonlinear buckling, post-elastic behavior, a pushover analysis is often used. This involves incrementally applying lateral loads to the structure until it reaches the point of failure or instability. 4. Modal analysis. Modal analysis helps to predict the buckling modes and corresponding critical loads for structures subjected to various boundary conditions. The first few modes are usually associated with the lowest critical buckling loads. 10.4. Buckling in structural design. Buckling analysis is integral to the design of slender elements, such as columns, beams, and plates. The design of structural members must ensure that the buckling load is greater than the maximum expected axial load. 1. Column design. Columns are designed by calculating the critical buckling load and ensuring that the applied axial load does not exceed this value. In reinforced concrete and steel columns, additional safety factors are applied to account for material imperfections and nonlinear behavior. 2. Plate and shell design. Plates and shells, particularly thin-walled members, must be designed to prevent local buckling. Reinforcements such as stiffeners or ribs may be added to increase the critical buckling load of a structure. 3. Bracing and lateral support. To prevent lateral torsional buckling, beams and other structural elements are often braced or restrained to maintain their stability during loading. Braces help reduce the effective length of the beam and increase its buckling resistance. 4. Impact of buckling on frame systems. In frame structures, the buckling of individual members may not immediately lead to failure. However, buckling failure in one member can cause redistribution of forces within the frame, potentially leading to failure in other parts of the system. Therefore, overall stability and frame stability must be considered in buckling analysis. Buckling is a critical failure mode for slender structural elements, and proper analysis is essential to ensure the safety and stability of structures under compressive loading. By understanding the types of buckling, the factors influencing buckling behavior, and the appropriate analysis methods, engineers can design more reliable and efficient structures. Advanced tools like finite element analysis, FEM, provide the means to analyze complex structures and determine the critical buckling load, which is vital for designing safe and durable buildings, bridges, and other infrastructure. 10. Advanced topics in structural analysis. Stability of structural systems. The stability of a structural system refers to its ability to maintain equilibrium under applied loads without undergoing undesirable or excessive deformations. Stability analysis is critical in ensuring that structures remain functional and safe during their service life, avoiding failure modes like buckling, collapse, or tipping. In structural engineering, stability analysis helps determine whether a system will experience elastic buckling, instability under lateral loads, or collapse due to material failure. A stable system remains within its elastic limits and doesn't experience unexpected deformations or instability under applied loads. On the other hand, an unstable system may experience a sudden and uncontrolled deformation, leading to failure. 10.1 Types of stability. 1. Geometric stability. Geometric stability deals with the shape or configuration of a structure and how it responds to applied loads. It is concerned with whether the structure's geometry allows for the transfer of loads without causing excessive displacements or collapse. A structural system is geometrically stable if it can resist deformations, such as buckling, and maintain its equilibrium despite external forces. 2. Material stability. Material stability refers to the behavior of the material under loading. Even if a structure is geometrically stable, material properties can influence the system's stability. For instance, a material may undergo plastic deformation, yielding, or fracture under extreme conditions, leading to instability. A structure may remain geometrically stable but fail due to material instability when the material cannot sustain the applied loads, e.g., yielding or brittle fracture. 3. Overall structural stability. Overall stability considers the interaction between both geometric and material stability. A structure can be geometrically stable but still fail due to material instability or a combination of both factors. This type of stability analysis includes global stability and local stability analysis. 10.2 Instability phenomena. 1. Elastic buckling. As discussed previously, buckling occurs when a slender structural element, such as a column, experiences a sudden lateral displacement under compressive axial loads. The critical buckling load represents the point where the structure becomes unstable. Global buckling occurs when an entire structural system loses stability, such as the buckling of a column or frame under compressive loads. 2. Instability due to lateral loads. Wind or earthquake. Lateral loads, such as wind or earthquake forces, can cause instability in structures, particularly if the structure lacks sufficient lateral support. This could lead to phenomena such as tipping, side sway, or collapse. Seismic stability is particularly important in regions subject to earthquakes. Engineers must ensure that structures are capable of resisting lateral forces and maintaining stability during seismic events. 3. P-delta effects. The P-delta effect refers to the additional moments and forces that develop in a structure as a result of its displacements under load. The vertical loads, P, acting on the structure create secondary moments as the structure displaces laterally, delta. This effect can lead to instability if the additional moments push the structure beyond its stable equilibrium. P-delta effects are especially important in tall buildings, towers, and frames under lateral loads like wind or seismic forces, as they can significantly reduce the stability of the structure. 4. Snap-through instability. Snap-through instability occurs when a structure experiences a sudden change in configuration due to a small disturbance or load. An example is thin plates or membranes that undergo large deformations and snap from one stable configuration to another. Nonlinear behavior typically dominates in snap-through instability, and it is essential to account for such effects in advanced structural analysis for sensitive structures such as shells and membranes. 10.3. Stability analysis methods. Several methods can be used to analyze the stability of structural systems, including linear and nonlinear methods, depending on the complexity of the structure and the type of instability being analyzed. 1. Linear stability analysis. In linear stability analysis, structures are assumed to behave elastically, and the system's response to small perturbations or disturbances is analyzed. This type of analysis involves eigenvalue problems to determine the critical load or buckling load and mode shapes, the deformation patterns under loading. Eigenvalue analysis in linear stability uses the stiffness matrix and mass matrix of a structure, yielding eigenvalues corresponding to the critical loads and the eigenvectors that define the mode shapes. 2. Nonlinear stability analysis. Nonlinear stability analysis accounts for large deformations, material plasticity, and geometric nonlinearities. Unlike linear analysis, this approach can model real-world behavior under extreme loading conditions. This analysis can be performed using finite element analysis, FEA, to capture nonlinear deformations and complex interactions between forces and displacements. 3. P-delta analysis. The P-delta effect is typically analyzed using second-order analysis, where the additional moments and forces due to displacements are included in the load deformation response of the structure. Nonlinear analysis tools can be used to accurately model and account for the P-delta effects in tall buildings and other structures subjected to large lateral forces. 4. Buckling and collapse analysis. Buckling analysis involves solving for the critical buckling load, which can be determined through methods like linear bifurcation analysis, nonlinear static analysis, or dynamic analysis, to account for time-dependent effects. Collapse analysis considers the entire load displacement path of a structure, particularly focusing on the post-buckling behavior. It includes load redistribution, plastic deformations, and the ultimate load capacity of the structure. 10.4. Stability of specific structural systems. 1. Structural frames. Frame structures are generally designed to resist both vertical and lateral loads. Stability analysis of frames must account for P-delta effects, the effect of lateral displacements on the axial loads in the frame members. Frame buckling. In frames with slender members, overall buckling or lateral torsional buckling of individual members must be considered. 2. Bridges. Bridges, particularly long-span structures, must undergo stability analysis to ensure they remain stable under traffic loads, wind forces, and thermal expansion. The lateral stability of bridges is critical to avoid tipping or side sway. Special consideration is given to cable-stayed bridges, suspension bridges, and arch bridges, which have unique stability challenges due to their geometry and load distribution. 3. Tall buildings. Tall buildings are particularly sensitive to lateral stability under wind and seismic loading. Stability analysis for high-rise buildings involves wind-induced sway, the lateral displacement of buildings due to wind forces, seismic stability, the building's ability to resist and absorb seismic forces, preventing collapse or large deformations. Interaction with foundations. The stability of a building must also consider the interaction with the foundation, particularly in soil structure interaction. 4. Shell and membrane structures. Shell structures and membrane structures are often thin and flexible, making them prone to snap through instability under load. Stability analysis involves modeling the large deformations of the structure and identifying any potential for collapse or instability due to lateral forces or thermal effects. 10.5. Practical considerations for structural stability. 1. Design for stability. Engineers must incorporate redundancy and reserve strength in designs to ensure that structures can resist unexpected forces and remain stable under loading. Bracing systems, e.g., shear walls, cross-bracing, are essential in providing lateral stability for buildings and bridges. 2. Nonlinear effects. Structures must be analyzed for nonlinear effects, such as material yielding, large deformations, and buckling under realistic loading conditions. Nonlinear analysis tools are essential for understanding the complex behavior of structures, especially in regions where extreme loading or large displacements occur. 3. Monitoring and maintenance. Structural health monitoring, SHM, is crucial in maintaining the stability of aging structures. Systems that measure displacements, strain, and temperature changes can help detect early signs of instability or failure. Regular maintenance and inspection are necessary to identify any degradation in structural elements, such as corrosion or fatigue, which may reduce stability over time. The stability of structural systems is a fundamental aspect of engineering design that ensures the safety and performance of structures under applied loads. Engineers must understand the different types of stability, the factors influencing stability, and the appropriate analysis methods to design stable structures. Advanced tools such as finite element analysis, FEA, and P-delta analysis provide powerful means of modeling and analyzing complex structural behavior under various load conditions, allowing for the design of safe and reliable structures that perform well throughout their service life. 10. Advanced topics in structural analysis. Post-buckling behavior and snap-through analysis. Post-buckling behavior and snap-through analysis are critical aspects of understanding how structures perform once they exceed their elastic limit and experience large deformations. These behaviors are especially important for structures that are prone to buckling, such as slender columns, plates, and shelves, as well as membrane structures. In these cases, the structure may not fail immediately after buckling, and it may still be able to carry loads through large nonlinear deformations. 10.1. Post-buckling behavior. Post-buckling behavior refers to the way a structure behaves after it has undergone buckling. After a structural element experiences a critical buckling load, the point at which it starts to lose stability, it may continue to deform, but it can still carry some load. The post-buckling region typically involves large, nonlinear deformations, and the structure's ability to carry additional loads may change drastically compared to its pre-buckling behavior. 1. Types of post-buckling behavior. Stable post-buckling. In this case, after buckling, the structure undergoes large displacements, but the load-carrying capacity increases or remains relatively constant as deformation progresses. Stable post-buckling behavior is seen in certain thin-walled structures like columns or plates. Example: a thin steel column may experience buckling, but with continued displacement, it can transfer additional loads through the nonlinear bending of its deformed shape. Unstable post-buckling. This occurs when, after buckling, the structure experiences a rapid decrease in load-carrying capacity. This situation is catastrophic, as the structure will undergo a collapse or complete failure after buckling. Unstable post-buckling behavior is more common in structures with insufficient load-bearing capacity after buckling. Example: A slender beam that experiences buckling may undergo rapid failure in the form of catastrophic collapse due to plastic deformation or fracture after reaching the buckled state. 2. Energy methods in post-buckling. In post-buckling analysis, energy methods are often used to assess the system's behavior. The strain energy stored in the structure before and after buckling is compared, and the system's potential energy is minimized to find the equilibrium configuration. The structure's load displacement curve is used to describe how the load carrying capacity changes in the post-buckling region. The curve typically shows a load drop after buckling if the behavior is unstable, or a load increase if the structure can continue to carry additional load. 3. Importance of post-buckling behavior. Post-buckling analysis is essential for safety-critical applications, such as in aerospace structures, bridges, and tall buildings, where the structure may experience significant loads after the initial buckling event. Designing structures to account for post-buckling behavior can improve their resilience and avoid catastrophic failure by ensuring that they can continue to carry loads beyond the point of initial instability. 10.2. Snap-through instability. Snap-through instability is a type of nonlinear behavior that occurs when a structure experiences a sudden and dramatic change in its configuration. Unlike typical buckling, where deformation is gradual and predictable, snap-through is characterized by a sharp transition between two stable equilibrium states, often caused by a small disturbance. 1. Mechanics of snap-through. Snap-through occurs when a system's load deformation curve has two or more local minima, representing stable equilibrium points. The structure starts in one stable configuration and, when perturbed beyond a critical point, snaps to another stable configuration. This phenomenon is common in structures that are preloaded or soft, such as thin-walled shells, membranes, and elastic systems. Energy considerations help explain the phenomenon. A system undergoing snap-through has stored potential energy that is released when the structure jumps from one configuration to another. 2. Snap-through in soft structures. Snap-through is particularly important in membrane and shell structures, where their soft nature and large deflections can lead to this sudden instability. Example: a curved membrane under uniform pressure might remain in one shape until a certain pressure is reached, after which it snaps to another, lower energy configuration. Inflated structures or tents are often designed to accommodate snap-through behavior. They rely on their pre-tensioned configurations to resist buckling, but snap-through may be a part of their design under high wind or pressure. 3. Applications of snap-through. Aerospace and space structures. In inflatable space structures, the snap-through behavior must be analyzed to ensure that the structure does not collapse or shift configuration unexpectedly. Civil engineering. In temporary or lightweight structures, such as tents or membranes, snap-through behavior is a key consideration in design. The structure must be able to handle large deformations without loss of integrity. 10.3. Analyzing post-buckling and snap-through. 1. Nonlinear analysis. Post-buckling and snap-through analysis require the use of nonlinear analysis techniques because the structure's deformation is large and cannot be captured by simple linear models. Finite element analysis, FEA, is commonly used to simulate and analyze these behaviors. Nonlinear FEA allows engineers to model large displacements, material nonlinearities, and geometric changes that occur after buckling. Arc length methods and load-controlled methods are typically used to track the behavior of the system beyond the buckling point and ensure that the path is properly traced in the post-buckling region. 2. Load deflection curves. Engineers use load deflection curves to assess the behavior of a structure beyond buckling. These curves show how the applied load and displacement evolve through the buckling and post-buckling regions. In stable post-buckling behavior, the curve shows an initial drop in load followed by an increase or flattening. In unstable post-buckling, the curve shows a significant load drop or sudden failure after buckling. 3. Bifurcation and snap-through. The bifurcation point is where the system transitions from one stable configuration to another. For snap-through analysis, bifurcation theory is used to identify when the system will switch between different equilibrium states under load changes. In snap-through analysis, engineers look for regions in the load deflection curve where there is a jump or sudden transition, indicating the occurrence of snap-through instability. 10.4. Practical considerations in design. 1. Structural safety. Understanding and accounting for post-buckling and snap-through behavior is crucial in preventing unexpected collapse or failure. Design codes for structural systems must consider these nonlinear behaviors, especially for slender elements or flexible structures. 2. Redundancy in design. Providing redundancy in structural systems, e.g., multiple load paths, can help mitigate the risks associated with snap-through and post-buckling behavior. Reinforcing critical structural elements or introducing additional support can prevent the structure from reaching a catastrophic point. 3. Control of snap-through. In some cases, snap-through may be intentional and used as part of the design for certain adaptive structures. For example, structures designed to fold or expand can use snap-through mechanisms as part of their functionality. However, for most structural applications, engineers aim to avoid undesirable snap-through behavior and design for stability after buckling. Post-buckling behavior and snap-through analysis are essential in advanced structural analysis, particularly for slender, flexible, or soft structures prone to large deformations. By understanding the potential for post-buckling stability and snap-through instability, engineers can design safer, more reliable structures that can withstand extreme conditions. Through the use of advanced nonlinear analysis techniques, such as finite element modeling, engineers can predict these behaviors and design structures to either accommodate or avoid them as needed. 11. Computational tools for structural analysis. Introduction to structural analysis software, e.g., SAP 2000, ETABS, ANSYS. In modern structural engineering, computational tools play a pivotal role in performing complex structural analysis tasks. These software programs help engineers simulate and analyze structures under various loads and conditions with high precision, efficiency, and accuracy. Structural analysis software enables engineers to model, analyze, and design structures in ways that were not possible with manual calculations alone. This section provides an overview of some of the most widely used structural analysis software, such as SAP 2000, ETABS, and ANSYS, along with their features, capabilities, and applications. 11.1. SAP 2000. SAP 2000 is one of the most popular and versatile general-purpose structural analysis and design software. It is widely used by structural engineers for modeling, analyzing, and designing a wide variety of structures, including buildings, bridges, dams, and industrial structures. 1. Key features of SAP 2000. Linear and nonlinear analysis. SAP 2000 can handle both linear and nonlinear static and dynamic analysis, making it suitable for a wide range of engineering problems. Finite element analysis, FEA. The software uses finite element methods to solve complex problems in structural mechanics. Engineers can model structures using various element types, such as beams, shelves, and solid elements. Dynamic analysis. SAP 2000 is equipped to perform dynamic analysis, including response spectrum, time history, and modal analysis. Design codes. SAP 2000 supports a wide variety of international design codes, including AISC, Eurocode, ACI, and ISC for structural elements, ensuring compliance with standards for material and structural strength. User interface. SAP 2000 offers a user-friendly graphical interface for model creation, data input, and result visualization. Engineers can easily input geometry, boundary conditions, and loads using an intuitive interface. 2. Applications of SAP 2000. Building design. Modeling of multi-story buildings in residential complexes with different types of loading conditions. Dead load, live load, seismic load, etc. Bridge analysis. Structural analysis of bridges and other transportation infrastructure, considering live loads, dynamic effects, and material properties. Industrial structures. Design and analysis of steel, concrete, and composite structures used in industrial plants and facilities. 3. Strengths. Broad application across different structural types and industries. Comprehensive analysis capabilities, including both linear and nonlinear problems. Easy-to-use interface and visualization tools for results. 11.2. ETABS. ETABS is a powerful structural analysis and design software developed by Computers and Structures, Incorporated, CSI. It is specifically tailored for the analysis and design of building structures, making it one of the most popular tools in high-rise building design and structural engineering for buildings. 1. Key features of ETABS. Integrated analysis and design. ETABS offers an integrated platform for both analysis and design of building structures, making it highly efficient for modern architectural and engineering designs. Building-specific tools. ETABS is optimized for multi-story building analysis, allowing users to easily model building elements such as floors, walls, columns, and slabs. Advanced seismic and wind analysis. The software includes advanced tools for seismic analysis and wind load determination, which are essential for earthquake-prone and high-wind regions. Nonlinear and dynamic analysis. ETABS supports various nonlinear analysis types, including time history analysis, response spectrum analysis, and pushover analysis, to model real-world scenarios under extreme conditions. Design codes. Like SAP 2000, ETABS also supports multiple design codes for buildings, including AISC, ACI, Eurocode, and IS 456. 2. Applications of ETABS. Tall building design. ETABS is widely used for the design of high-rise buildings and skyscrapers, particularly when considering complex loadings, lateral forces, and dynamic behavior. Seismic design. The software provides a robust environment for analyzing buildings subjected to seismic forces and other dynamic loads, helping engineers design structures to withstand earthquakes and aftershocks. 3. Strengths. Highly specialized for building structures, especially tall and complex buildings. Strong seismic and wind load analysis features. Integrated design tools that help engineers perform analysis and design in one environment. 11.3. ANSYS. ANSYS is a multiphysics simulation software that is widely used for advanced structural analysis, thermal analysis, and fluid dynamics. It is a powerful tool for solving complex engineering problems across various domains, including aerospace, automotive, civil, and mechanical engineering. 1. Key features of ANSYS. Advanced Finite Element Analysis, FEA. ANSYS offers a comprehensive suite of tools for performing linear and nonlinear FEA on structures, materials, and components. Multiphysics simulations. In addition to structural analysis, ANSYS supports multiphysics simulations, enabling engineers to analyze coupled phenomena such as thermal stress, fluid structure interaction, and electromagnetic fields. Material modeling. ANSYS includes extensive libraries for modeling a wide range of materials, including metals, polymers, composites, and more, allowing engineers to perform simulations with high accuracy. Optimization and simulation-based design. ANSYS offers advanced tools for optimizing designs based on performance criteria, helping engineers make better decisions in the design phase. Large-scale simulations. ANSYS can handle large-scale simulations of complex systems, making it suitable for industries such as aerospace and automotive, where high-fidelity modeling is required. 2. Applications of ANSYS. Aerospace. ANSYS is used to simulate aerospace structures under extreme conditions, such as high-speed airflow, pressure, and thermal gradients. Automotive. Engineers use ANSYS for crash simulations, durability analysis, and multiphysics simulations involving vibration and heat transfer. Civil engineering. For advanced structural problems, ANSYS is used to simulate the response of buildings, bridges, and infrastructure under complex loading conditions. 3. Strengths. Multiphysics capabilities make it suitable for simulations beyond structural analysis, such as thermal, electromagnetic, and fluid dynamics. Highly detailed simulations of complex systems with multi-material interactions. Optimization capabilities for improving design efficiency and performance. 11.4. Comparison of SAP 2000, ETABS, and ANSYS. Software. Key strengths. Best for. Main use cases. SAP 2000. General purpose, versatile, and user-friendly. General structural analysis, civil engineering, and industrial applications. Building design, bridges, dams, and industrial structures. ETABS. Specialized in building design and seismic analysis. High-rise buildings, multi-story structures, and seismic applications. Tall building design, seismic and wind load analysis. ANSYS. Multiphysics and complex simulations. Complex simulations in aerospace, automotive, and civil engineering. Advanced structural, thermal, and multiphysics simulations. Structural analysis software is an indispensable tool in modern engineering practice. Programs like SAP 2000, ETABS, and ANSYS provide engineers with the tools needed to perform accurate, efficient, and comprehensive analysis of structures under a wide variety of loading conditions. Each software package has its strengths and specialized applications, and selecting the appropriate tool depends on the specific project requirements. By leveraging these advanced computational tools, engineers can ensure that their designs are optimized for safety, performance, and cost-effectiveness. 11. Computational tools for structural analysis. Modeling techniques and assumptions. The use of computational tools such as SAP 2000, ETABS, ANSYS, and others relies heavily on accurate modeling techniques and assumptions that simplify complex real-world systems into manageable and solvable models. These techniques are fundamental in obtaining reliable results and ensuring that the analysis of structures represents real-world behavior as closely as possible. However, engineers must make assumptions to balance computational efficiency and accuracy. This section discusses the modeling techniques and assumptions commonly used in computational structural analysis. 11.1. Modeling techniques in structural analysis. Modeling involves representing a physical structure mathematically within a software environment. The accuracy of the model significantly impacts the quality and reliability of the results. 1. Finite element modeling. FEM. Finite element modeling, FEM, is the most commonly used method in computational structural analysis. It divides a structure into smaller, simpler elements called finite elements, which are connected at nodes. The behavior of each element is described using a set of equations, and the overall behavior of the structure is found by solving the system of equations for all elements. Element types. Depending on the type of analysis and geometry, different types of finite elements are used, including beam elements, for one-dimensional structural elements like beams, columns, and trusses. Shell elements, for thin structures like plates and slabs that have bending and membrane behaviors. Solid elements, for three-dimensional structures, where full volumetric analysis is required. Truss elements, for modeling structures that carry loads primarily through axial forces. Mesh generation. In FEM, the mesh refers to the discretization of the structure into smaller elements. A fine mesh, more elements, leads to more accurate results but increases computational time. A coarse mesh is faster but less accurate. Boundary conditions. Proper boundary conditions are critical in structural modeling. This includes defining the structure's supports, constraints, and load applications, e.g., fixed supports, rollers, or pinned supports. 2. Idealization of materials. Material properties must be modeled accurately for realistic results. Depending on the assumptions made about the material behavior, different material models can be used in the analysis. Linear elastic material. In most cases, materials are assumed to behave elastically within the limits of their strength. Young's modulus and Poisson's ratio are the primary parameters used to define the material behavior. Nonlinear materials. For more complex scenarios where materials may exhibit plastic behavior, cracking, or other nonlinear phenomena, material models such as plasticity models or damage models can be implemented. 3. Structural idealization. In structural analysis, engineers often simplify complex structures by idealizing them as beam column systems, frame structures, or other simpler models. This idealization involves reducing 3D models to 2D or 1D models. In some cases, a 3D structure can be simplified to a 2D plane frame or even a 1D line model, reducing computational complexity. Ignoring small details. Small features like small notches, holes, or welds might be neglected unless they significantly affect the overall strength or stability of the structure. 4. Load application modeling. Loads on a structure are typically applied as concentrated loads, distributed loads, or temperature changes, depending on the scenario. Computational tools can simulate these loads in various ways. Point loads. These are applied at specific nodes or points of the structure. Distributed loads. These represent loads spread over an area, such as pressure or wind forces, and are applied to surfaces or line elements. Time-dependent loads. Dynamic and transient loads, such as seismic, wind, or traffic loads, can be applied in time history or response spectrum analyses. 11.2. Assumptions in computational structural analysis. When modeling structures, several simplifications and assumptions are made to ensure the analysis is feasible and the results are computationally efficient. These assumptions are often necessary to simplify the complexity of real-world behavior. 1. Linear versus nonlinear behavior. Linear assumption. The most common assumption is that the structure behaves linearly, which means that stress is proportional to strain, Hooke's law. The material remains elastic, and the deformations are small, i.e., within the elastic limit. The structure's response remains proportional to the applied loads. No changes in stiffness due to deformation. This assumption simplifies the problem and makes it solvable using methods such as linear finite element analysis, FEA. However, for large deformations, plasticity, or brittle material behavior, nonlinear analysis is required. Nonlinear assumption. For more complex scenarios where the material or structure may experience plastic deformation, yielding, buckling and snap-through behavior, or geometrically nonlinear behavior, large deformations, nonlinear analysis becomes necessary. However, nonlinear models are computationally more intensive. 2. Perfectly elastic materials. For the sake of simplicity, many models assume perfectly elastic behavior, where no permanent deformation occurs. This is common in the linear elastic modeling used in most structural analysis software. However, real materials can exhibit some plasticity, creep, or fatigue effects, which may need to be considered in specialized analyses. 3. Idealized support conditions. Support conditions are often assumed to be perfectly rigid, fixed, or perfectly flexible, roller. In reality, support settlement or foundation stiffness may vary, but these complexities are often ignored in initial models to simplify the calculations. 4. Idealized load distribution. Loads are often idealized as uniformly distributed point loads, or triangular loads based on theoretical models or approximations. In practice, loads may not be perfectly uniform and could vary in magnitude or direction. For example, wind loads or earthquake forces are idealized based on certain assumptions about the directionality and magnitude of the forces. 5. Material homogeneity and isotropy. Many structural models assume that materials are homogeneous. Properties are uniform throughout the material. And isotropic. Properties are the same in all directions. In reality, materials like composites and geotechnical materials may be anisotropic. Properties vary with direction, or heterogeneous, having different properties at different locations. 6. Small deformations. Linear elastic. Most basic analyses assume that the deformations are small enough that linear elastic theory applies. This means that the relationship between applied loads and deformations is proportional, and no large-scale deformations or changes in the structure's geometry are considered. For large deflections, a nonlinear analysis may be required, as this assumption becomes invalid. 11.3. Model validation and refinement. Once a structure is modeled and the initial analysis is performed, the results need to be validated and refined. Validation. This involves comparing the computational results with experimental data or analytical solutions for similar problems. Benchmark tests, e.g., simple problems with known solutions, are often used to validate the accuracy of the computational model. Refinement. After the initial analysis, engineers may refine the model by improving the mesh density, especially in areas of high stress concentration, using more advanced material models for nonlinear analysis, adjusting boundary conditions or load assumptions to better reflect reality. The accuracy and reliability of computational structural analysis depend heavily on the modeling techniques and assumptions made during the process. By choosing appropriate element types, material models, and boundary conditions, engineers can create simplified representations of real-world structures that allow for efficient and accurate analyses. However, engineers must always be aware of the assumptions made during the modeling process, as these can affect the quality of the results. Model validation and refinement are key steps to ensuring that the computational results closely match the behavior of actual structures. 11. Computational tools for structural analysis. Practical applications and case studies. In the field of structural engineering, computational tools play a crucial role in designing, analyzing, and optimizing structures for various real-world applications. The use of software tools such as SAP 2000, ETABS, and ANSYS has revolutionized the way engineers approach complex structural problems, allowing for more accurate, efficient, and safe designs. This section explores practical applications and case studies where these tools have been successfully used to analyze and solve real-world engineering challenges. 11.1. Application in building design. 1. Tall building design and seismic analysis with ETABS. Case study: the Burj Khalifa in Dubai. The Burj Khalifa is one of the tallest buildings in the world, standing at 828 meters. It serves as an excellent example of how computational tools like ETABS can be used for dynamic analysis and wind/earthquake load calculations for high-rise buildings. Challenges: the design team faced the challenges of wind load, seismic loads, and lateral forces from the extreme height and location in an earthquake-prone region. Solution: ETABS was used to model the building's structure, taking into account the complex interaction of wind pressures, dynamic loads, and vibration modes. ETABS was employed to simulate how the building would respond to earthquake forces and wind-induced sway to ensure the structure could withstand such loads without compromising safety or comfort. Outcome: by performing dynamic analysis and using the software's response spectrum and time history analysis capabilities, the engineers ensured that the design was robust and adhered to international seismic standards. 2. Residential building design with SAP 2000. Case study: mid-range residential building. For residential buildings, SAP 2000 is commonly used to carry out structural analysis for load-bearing systems, including beams, columns, and slabs. Challenges: in a typical mid-rise residential project, the design team needed to analyze the overall structural behavior, considering dead load, live load, and lateral loads such as wind forces. Solution: the project team used SAP 2000 to develop the structural model, with linear static analysis to determine the internal forces and moments in structural elements. In addition, the software's automatic code compliance features allowed for the analysis and design to conform to local building codes. Outcome: by using SAP 2000, the team optimized the design of the foundation and the superstructure, ensuring material efficiency while maintaining the safety and stability of the building. The software helped streamline the design process, reducing the need for manual calculations and ensuring a faster project delivery. 11.2. Application in bridge design. 1. Bridge analysis and design with SAP 2000. Case study: Golden Gate Bridge, seismic retrofit. The Golden Gate Bridge in San Francisco is an iconic structure that has undergone several updates and retrofitting to ensure its stability, especially against seismic risks. Computational tools like SAP 2000 are widely used in the design and retrofitting of bridges, particularly in the analysis of dynamic loads and structural stability. Challenges. The Golden Gate Bridge was found to have vulnerabilities due to earthquake-induced forces and the increasing traffic load. The challenge was to retrofit the bridge's support structure to withstand modern seismic forces. Solution. The engineering team used SAP 2000 to model the bridge, perform dynamic seismic analysis, and simulate how the structure would respond to earthquake shaking. By incorporating dynamic effects, soil structure interaction, and foundation flexibility into the model, the team was able to design a retrofit plan that would increase the bridge's earthquake resistance. Outcome. The retrofit design successfully improved the bridge's seismic performance, ensuring its longevity and safety. Using SAP 2000 allowed for a comprehensive analysis and simulation of how the bridge would behave under extreme seismic events, leading to a cost-effective and safe solution. 2. Load distribution in bridges with ANSYS. Case study. Suspension bridge load analysis. A large-scale suspension bridge was being designed to accommodate high traffic volume and extreme weather conditions. ANSYS was employed to simulate the load distribution across the structure, particularly in the cables, deck, and towers. Challenges. The primary challenge was modeling the nonlinear behavior of the cables and deck, particularly under high dynamic loads such as traffic and wind forces. Solution. Using ANSYS, the team created a 3D finite element model of the entire suspension bridge. The nonlinear material properties of the cables and deck were considered, and dynamic loads from traffic, wind, and seismic events were simulated. Outcome. The analysis revealed the stress distribution across the bridge, allowing engineers to design an efficient and safe load-bearing system. ANSYS also helped optimize the design of the cable and the suspension towers, ensuring the bridge could carry its intended load without exceeding material strength limits. 11.3. Application in industrial and aerospace engineering. 1. Aircraft structural analysis with ANSYS. Case study. Airbus A380 wing design. The design and stress analysis of an aircraft wing, such as those used in the Airbus A380, involves solving complex structural problems under dynamic loading, including aerodynamic forces, fatigue, and thermal stresses. Challenges. The design of an aircraft wing must ensure that it can withstand high aerodynamic loads, vibrations from engine thrust, and fatigue from repeated flight cycles. Solution. ANSYS was used to simulate the wing's structural integrity by performing fatigue analysis, vibration analysis, and thermal analysis. The team employed finite element analysis, FEA, to model the wing structure, considering material properties, manufacturing tolerances, and load conditions. Outcome. The computational analysis provided crucial insights into potential failure points, enabling the engineers to refine the design for optimal strength and durability. The use of ANSYS allowed for precise prediction of the wing's performance, ensuring the safety and reliability of the Airbus A380. 11.4. Application in seismic engineering. 1. Seismic design of buildings with ETABS. Case study. Earthquake-resistant skyscraper in Tokyo. Tokyo is located in an area highly prone to earthquakes, and thus, designing earthquake-resistant structures is a critical part of the city's construction projects. ETABS is widely used to perform seismic analysis of high-rise buildings. Challenges. The design of a skyscraper in Tokyo needed to withstand the intense seismic forces that are characteristic of the region. Solution. ETABS was used to model the building's structural response to earthquakes. The software helped simulate the building's vibration modes, assess the response to seismic loads, and ensure safety under extreme conditions. Outcome: using ETABS, the design team was able to optimize the building's lateral resistance system, e.g., shear walls, bracing, and damping systems, ensuring that the skyscraper could resist the seismic forces while minimizing the risk of structural failure. Computational tools for structural analysis have transformed the way engineers approach complex design and analysis problems. From high-rise buildings to suspension bridges and aircraft, these tools enable precise modeling, optimization, and validation of structural designs. The real-world applications and case studies discussed demonstrate the crucial role of software in addressing engineering challenges and ensuring the safety, efficiency, and sustainability of structures across various industries. These tools not only help improve the design process but also contribute to advancing engineering practices and technologies. 12. Applications of advanced structural analysis. Bridge and tall building design. Advanced structural analysis methods are crucial in the design of both bridges and tall buildings, as these structures are subject to complex forces and interactions. Engineers use state-of-the-art computational tools and advanced analysis techniques to ensure that these structures are safe, stable, and efficient. Below is a detailed exploration of how advanced structural analysis is applied to bridge and tall building design. 12.1. Bridge design. Bridges are critical infrastructure components that need to withstand dynamic loads, environmental conditions, and traffic-related forces. Advanced structural analysis plays a vital role in ensuring that bridges can handle these stresses and remain durable over time. 1. Dynamic load analysis in bridges. Case study: Golden Gate Bridge seismic retrofit. Challenges: the Golden Gate Bridge is located in a seismically active area, and its structure needed to be retrofitted to meet modern seismic standards. Earthquake forces pose a significant challenge for bridges, especially those that were originally designed before modern seismic design codes were developed. Advanced analysis. Computational tools like SAP 2000 or ANSYS were used to perform dynamic analysis of the bridge. These tools help simulate seismic load scenarios and assess how the bridge's structure will respond to earthquake forces. Nonlinear time history analysis and response spectrum analysis were employed to model ground motion and simulate the bridge's dynamic response. Outcome: the seismic retrofit project involved strengthening the bridge's supports and incorporating damping systems to reduce seismic vibrations. Advanced dynamic modeling ensured that the design met modern seismic requirements, improving the safety and longevity of the bridge. 2. Load distribution and stress analysis in bridges. Case study: Akashi Kaikyo Bridge, Japan. Challenges: the Akashi Kaikyo Bridge, the world's longest suspension bridge, was designed to carry massive traffic loads, including wind-induced forces and seismic forces. Advanced analysis. Structural engineers used advanced finite element analysis (FEA) tools, such as ANSYS, to simulate load distribution and stress behavior across the bridge. Nonlinear static and dynamic analyses were performed to account for the complex interactions between the deck, suspension cables, and towers. Outcome: the analysis ensured that the bridge could withstand extreme conditions such as high wind speeds and earthquake activity. Additionally, by analyzing stress concentrations, the team optimized the design of the bridge's components for better material usage and cost-effectiveness. 3. Fatigue and durability analysis of bridges. Case study: I-35W Mississippi River Bridge, USA. Challenges: the I-35W Mississippi River Bridge collapsed in 2007 due to fatigue failure of its structural components. This highlighted the importance of fatigue analysis in bridge design, particularly for older bridges subjected to heavy traffic and environmental stressors. Advanced analysis. Fatigue analysis was performed using advanced structural analysis tools like SAP 2000 to simulate long-term stress cycling in the bridge's components, particularly in welded joints and connection points. Engineers examined the life cycle behavior of materials and assessed the structure's ability to withstand repetitive loading over time. Outcome: modern bridge design codes now require detailed fatigue analysis, ensuring that structures are capable of handling prolonged wear and tear without catastrophic failure. 12.2. Tall building design. Tall buildings, skyscrapers, are subject to unique challenges, such as wind loads, seismic forces, and dynamic interactions. Advanced structural analysis methods are essential for designing these complex structures, ensuring their stability, safety, and performance under a variety of load conditions. 1. Wind and earthquake load analysis for tall buildings. Case study: Burj Khalifa, Dubai. Challenges: the Burj Khalifa is the tallest building in the world, and its design had to account for extreme wind loads, seismic forces, and the building's height-induced dynamic behavior. Advanced analysis. Tools like ATABS and SAP 2000 were used to model the building's structural response to wind-induced lateral forces, which are particularly important for skyscrapers. Engineers used wind tunnel testing combined with computational fluid dynamics (CFD) simulations to determine wind pressure distributions on the building's surface. Additionally, seismic analysis ensured the building's stability in the event of an earthquake. Outcome: by incorporating dynamic analysis and wind load simulations, the engineers optimized the building's design, particularly the structural frame, shear walls, and damping systems. The Burj Khalifa's tuned mass damper was designed to reduce vibrations caused by wind, ensuring comfort for occupants and preventing structural damage. 2. Structural systems for tall buildings. Case study: Willis Tower, Chicago. Challenges: the Willis Tower, formerly Sears Tower, in Chicago is one of the tallest buildings in the U.S., and its design required careful consideration of lateral stability, particularly in high wind areas. Advanced analysis. ATABS was used to design the building's lateral load-resisting systems, which included a combination of moment-resisting frames, shear walls, and bracing systems. The team performed a nonlinear dynamic analysis to simulate how the building would respond to wind loads and earthquake motions. Outcome: the final design included a twin tower configuration with a core and outrigger system for increased stability. This design ensured the building could withstand lateral forces while maintaining an efficient use of space and materials. 3. Performance-based design and optimization for skyscrapers. Case study: Shanghai Tower, China. Challenges: the Shanghai Tower is China's tallest building and needed to accommodate earthquake and wind loads, as well as provide optimal energy efficiency and occupant comfort. Advanced analysis. Performance-based design principles were used in combination with finite element analysis (FEA) and dynamic response analysis to evaluate the building's response to wind forces and earthquake motion. Advanced tools like ANSYS and SAP 2000 helped model the building's aerodynamic shape, while also analyzing its structural systems under extreme loads. Outcome: the building's design was optimized for aerodynamic performance, minimizing wind-induced sway and reducing energy consumption. The structural design incorporated viscous dampers to reduce vibrations and enhance the building's overall performance. 4. Sustainability and material efficiency in tall building design. Case study: One World Trade Center, New York. Challenges: The One World Trade Center had to be designed not only for safety and stability but also for sustainability. The building's design required advanced methods for minimizing material use while ensuring structural efficiency. Advanced analysis. Computational tools like ETABS and ANSYS were used to simulate various load conditions and optimize the design for material efficiency. Structural engineers performed a sustainability assessment to minimize the carbon footprint of the building, focusing on recycled materials, energy-efficient systems, and minimal material wastage. Outcome. The final design included a high-performance structural system that provided both resilience and sustainability, achieving the goal of reducing the overall environmental impact of the building. The application of advanced structural analysis in bridge and tall building design is essential for creating safe, efficient, and sustainable structures. These advanced techniques enable engineers to account for a wide variety of loads, including dynamic forces, wind and seismic forces, and fatigue, all while optimizing the use of materials and enhancing the structure's performance over its lifespan. By employing tools like ETABS, SAP 2000, ANSYS, and other advanced software, engineers can model and simulate complex interactions within the structure, leading to innovative solutions for modern infrastructure challenges. As engineering technology continues to evolve, the role of advanced structural analysis in ensuring the safety, performance, and sustainability of bridges and tall buildings will only continue to grow. 12. Applications of advanced structural analysis. Space structures and aerospace applications. Advanced structural analysis plays a critical role in the design, analysis, and optimization of space structures and aerospace applications, as these structures must withstand extreme environmental conditions, high dynamic loads, and significant material stresses. Engineers use advanced methods and computational tools to simulate and assess the performance of spacecraft, satellites, and aircraft to ensure that they can operate effectively and safely in the harshest environments, including the vacuum of space, high speeds, and intense thermal and mechanical loads. 12.1. Space structures. Space structures include satellites, space stations, and spacecraft that must be designed to endure extreme conditions such as microgravity, vacuum, radiation, and thermal gradients. Structural integrity is critical for these systems to survive the rigors of launch, space travel, and re-entry. 1. Design of satellite structures. Case study. Hubble Space Telescope. Challenges. The Hubble Space Telescope, HST, launched in 1990, required a highly precise and durable structure capable of withstanding the launch forces and thermal expansion in space. The structure had to maintain its alignment and optical precision over many years. Advanced analysis. Engineers used advanced finite element analysis, FEA, and thermal analysis to simulate the structural behavior of the telescope under different loading conditions, including launch vibrations, thermal fluctuations, and microgravity effects. Tools like ANSYS and EBACUS were employed to assess thermal stress and dynamic response during launch and the space environment. Outcome. The telescope was equipped with precise structural components that ensured the optical system remained aligned in space, even when subjected to temperature changes and vibrations. The structural analysis ensured the telescope's longevity and functionality in orbits. 2. Spacecraft structural integrity. Case study. Mars rovers. Spirit, Opportunity, Curiosity. Challenges. The Mars rovers, such as Spirit and Opportunity, required rugged and reliable structural designs to handle the harsh Martian environment, including extreme temperature variations, dust storms, and vibrations during landing. Advanced analysis. Engineers used advanced tools such as abacus and ANSYS to model the rover's structural integrity under the impact of landing forces, temperature gradients, and radiation. Thermal analysis was critical to simulate the temperature extremes on Mars, ensuring that materials would not degrade in the hostile environment. Outcome: the structural analysis ensured the rovers were able to survive their landings, operate effectively on the Martian surface, and endure the stresses of movement and environmental conditions, leading to the successful missions of both Spirit and Opportunity, which lasted far beyond their expected lifetimes. 3. Space stations and habitats. Case study: International Space Station, ISS. Challenges: the International Space Station, ISS, is a long-duration platform in low Earth orbit, and its structure must withstand microgravity forces, space radiation, thermal expansion, and launch and docking loads from spacecraft. Advanced analysis: advanced finite element methods, FEM, and thermal models were used to design the space station's structural components. Tools like abacus and ANSYS helped model the complex interactions between the various modules and ensure the ISS could handle dynamic loads during docking operations. Additionally, thermal analysis helped design components that would maintain thermal stability despite extreme temperature fluctuations in space. Outcome: the ISS was built using lightweight, yet strong materials like aluminum and titanium alloys, ensuring that it could support the weight of astronauts, experiments, and other payloads. The station's design successfully met the structural demands of space, providing a stable environment for scientific research. 12.2. Aerospace applications. In aerospace engineering, aircraft structures must be designed to withstand a variety of forces, including aerodynamic loads, thermal stresses, fatigue, and vibration from high-speed flight. Advanced structural analysis ensures the safety, efficiency, and performance of these aircraft, whether they are commercial airliners, military jets, or spacecraft. 1. Aircraft structural design. Case study: Boeing 787 Dreamliner. Challenges: the Boeing 787 Dreamliner is a modern commercial airliner that must endure fatigue from frequent flight cycles, aerodynamic loads, and thermal stresses. Additionally, the Dreamliner uses composite materials that are subject to different behavior compared to traditional metals. Advanced analysis: engineers used ANSYS, abacus, and MSc Nastrand to perform fatigue analysis, aeroelastic analysis, and thermal modeling of the aircraft's structure. The tools helped simulate the complex interactions of loads experienced during takeoff, flight, and landing, including pressure distribution, vibration modes, and temperature changes. Outcome: advanced analysis ensured that the Boeing 787 could withstand the repeated stresses of flight and operate safely at higher altitudes and lower pressures. The use of composite materials was optimized for lightweight strength, improving fuel efficiency while ensuring long-term durability. 2. Wing design and load distribution in aircraft. Case study: Airbus A380 wing design. Challenges: the Airbus A380, the world's largest passenger airliner, required a highly efficient and durable wing structure capable of supporting its large weight, while withstanding aerodynamic forces and vibration during flight. Advanced analysis: engineers used finite element analysis, FEA, to model the load distribution and stress concentrations across the wing structure. Tools like ANSYS and abacus helped simulate the dynamic response of the wings to aerodynamic forces, ensuring the structure could handle fatigue and impact loads. Stress tests were performed to evaluate the wing's performance under extreme conditions, including high-speed flight and landing loads. Outcome: the A380's wing design incorporated advanced composite materials and load-bearing structures optimized to handle the dynamic loads of the aircraft. The wing's structural integrity ensures the safe operation of the largest airliner in commercial aviation. 12.3 Spacecraft Launch and Re-Entry Design. Case Study: Space Shuttle Re-Entry Hatch Shield Design. Challenges: the Space Shuttle had to survive the intense heat and aerodynamic loads during re-entry into Earth's atmosphere, with temperatures reaching up to 1,500 degrees C, 2,732 degrees F. The hatch shield was crucial for protecting the spacecraft and crew from the extreme re-entry conditions. Advanced analysis. Thermal analysis was essential to design the hatch shield, which consisted of carbon-based tiles that could withstand high temperatures. Advanced heat transfer simulations using ANSYS and Abaqus helped determine the heat distribution and thermal stresses during re-entry. Aerodynamic analysis ensured the hatch shield would maintain stability and performance under high-speed flight conditions. Outcome: the hatch shield successfully protected the Space Shuttle during re-entry, allowing for safe landings after missions. The analysis of thermal stresses and aerodynamic forces ensured the shuttle's structural integrity during its most challenging phase of flight. In both space structures and aerospace applications, advanced structural analysis is essential for ensuring the performance, safety, and durability of these highly complex and often mission-critical systems. Whether it's designing satellite structures that need to endure the vacuum of space or optimizing the wing structure of a large aircraft, computational tools like ANSYS, Abaqus, and MSc Nastran are vital for simulating and evaluating a wide range of loads, stresses, and dynamic conditions. By utilizing advanced finite element analysis, thermal simulations, and dynamic modeling, engineers can ensure that space structures and aerospace vehicles perform reliably, even under the most extreme conditions. As technology advances, these methods will continue to evolve, leading to the development of more efficient, safer, and sustainable aerospace and space technologies. 12. Applications of advanced structural analysis. Seismic and wind load design. In the design of buildings and infrastructure, the analysis of seismic, earthquake, and wind loads is critical for ensuring safety and stability. These loads can induce significant forces on structures, and advanced structural analysis methods are employed to predict the behavior of structures under these dynamic forces. Proper design for seismic and wind loads is crucial in regions prone to natural hazards, ensuring the structural integrity of buildings, bridges, and other infrastructure. 12.1 Seismic load design. Seismic loads are forces generated by the earthquake ground motions that can cause building displacement, deformation, and potentially lead to structural failure. Structures in seismically active regions must be designed to resist the dynamic forces generated by earthquakes. 1. Seismic load analysis. Case study. Design of buildings in earthquake-prone areas, e.g., San Francisco, California. Challenges. Buildings in earthquake-prone regions need to be able to withstand the horizontal and vertical shaking caused by seismic activity. The forces can vary greatly depending on the magnitude of the earthquake, the distance from the epicenter, and the local soil conditions. A uniform building design is inadequate for earthquake resistance. Rather, each structure must be tailored to its specific environment. Advanced analysis, response spectrum analysis, time history analysis, and linear/nonlinear dynamic analysis are commonly used methods to assess the structural response to seismic loads. Engineers model dynamic behavior using finite element analysis, FEA, software such as ANSYS or SAP 2000 to simulate earthquake-induced vibrations and displacements. Outcome: the dynamic analysis ensures that buildings can resist seismic forces and minimize damage during an earthquake. For example, base isolation systems can be used to decouple the building from ground motions, allowing the structure to move independently of the foundation. 2. Seismic design code compliance. In addition to advanced analysis, building codes provide guidelines on how to design for seismic forces. For instance, in the U.S., the International Building Code, IBC, and the ASCE 7 standards specify minimum seismic design requirements based on the building's location, size, and importance. Key considerations: building importance factor, higher importance for hospitals, schools, etc. Seismic design categories, SDC, ranges from a low seismic risk to F, high seismic risk. Load combinations. Seismic forces are considered in conjunction with dead, live, snow, and wind loads. 12.2. Wind load design. Wind loads are forces exerted on structures by the movement of air. The design of buildings, especially tall structures, bridges, and rooftop equipment, must account for the wind forces they will encounter under both static and dynamic conditions. 1. Wind load analysis. Case study: wind load design of skyscrapers, e.g., Burj Khalifa, Dubai. Challenges: tall buildings and structures like the Burj Khalifa must resist lateral forces generated by strong winds, particularly in areas subject to hurricane-force winds. These forces act across the building's surface area, inducing vibrations, deflections, and shear stresses. Advanced analysis. To evaluate the aeroelastic response of the structure, computational fluid dynamics, CFD, and wind tunnel testing are used. Dynamic analysis using finite element modeling helps simulate how the building responds to different wind speeds and directional forces. Modal analysis is often employed to ensure the building's fundamental frequency does not match the wind's frequency, which could cause resonance and significant structural damage. Outcome: tuned mass dampers, which are designed to reduce the amplitude of structural vibrations, are often incorporated into skyscrapers to counteract the effects of wind-induced motion. Advanced modeling ensures that the Burj Khalifa and similar structures are capable of handling wind forces safely and effectively. 2. Wind load code compliance. Wind load design also follows established building codes, such as ASCE 7, Eurocode 1, and the International Building Code, IBC. These codes specify methods to calculate the wind pressure and the building's structural response to wind forces. Key factors for wind load design. Basic wind speed, determined based on geographical location and historical wind data. Exposure category, accounts for the surrounding environment, open terrain, urban areas, etc. Importance factor, similar to seismic design, critical buildings require a higher safety factor. Wind directionality factor, determines how wind interacts with the building at different angles. 12.3. Combined seismic and wind load analysis. In many regions, both seismic and wind loads must be considered in the design of a structure, especially in coastal or hurricane-prone areas where earthquakes and strong winds can occur simultaneously or in close succession. 1. Load combination and interaction. Challenges. Structures need to be designed to withstand combined loads, including seismic and wind forces, simultaneously or sequentially. Advanced analysis methods ensure that the structure will not fail due to any one type of loading. Advanced analysis. Engineers often use multi-hazard analysis to evaluate how a structure behaves under combined seismic and wind loads. This involves stochastic simulations, Monte Carlo methods, and nonlinear dynamic analysis to understand the interaction between these forces. Outcome. The structural design incorporates safety features that account for both seismic and wind-induced displacements to minimize the likelihood of failure under extreme conditions. The analysis results in a more resilient structure capable of performing well in both seismic events and extreme wind conditions. Advanced structural analysis plays an essential role in the design of structures subject to seismic and wind loads, helping engineers ensure the safety, functionality, and resilience of buildings and infrastructure. By employing techniques such as finite element analysis, dynamic simulations, and response spectrum analysis, engineers can accurately model how structures will behave under dynamic loading conditions and optimize their designs for strength, stability, and comfort. The application of structural design codes alongside advanced computational methods allows for the creation of safe and efficient buildings, bridges, and other critical infrastructure, even in the most hazardous regions. These analysis techniques continue to evolve, making it possible to design structures that not only meet safety requirements but also enhance performance and sustainability in an increasingly dynamic world. 12. Applications of advanced structural analysis. Energy absorption and safety considerations. In structural engineering, energy absorption plays a crucial role in enhancing the safety of buildings, bridges, and other structures under extreme load conditions such as earthquakes, windstorms, impact loads, and blasts. The goal is to design structures that can absorb and dissipate energy during these events, thereby reducing the forces transferred to the structure and increasing safety for occupants and the surrounding environment. Advanced structural analysis is essential in designing energy-absorbing systems and ensuring the resilience of structures under dynamic loadings. 12.1. Energy absorption in seismic design. In the case of earthquakes, the kinetic energy generated by ground motion must be dissipated by the structure to prevent damage and failure. Buildings must be designed to resist the dynamic effects of earthquake forces, while also absorbing some of the energy through structural elements that can deform and dissipate energy without catastrophic failure. 1. Seismic dampers and energy dissipation systems. Case study. Use of dampers in high-rise buildings, e.g. Taipei 101, Taiwan. Challenges. Tall buildings like Taipei 101 in a seismic zone face challenges related to wind and earthquake loads. The building's slenderness ratio makes it more susceptible to dynamic motion caused by seismic forces. Advanced design. To reduce the effects of seismic shaking, engineers incorporate energy dissipation systems such as viscous dampers, tuned mass dampers, and friction dampers. These devices absorb a significant portion of the seismic energy, preventing the structural elements from experiencing excessive deformation. Viscous dampers use fluid to absorb and dissipate energy through resistance to motion, reducing vibration. Tuned mass dampers, often placed in the building's upper floors, counteract the building's motion by generating an opposing force. Friction dampers convert kinetic energy into heat through friction, reducing motion. Outcome. These advanced design techniques allow structures like Taipei 101 to withstand strong earthquakes and wind forces by efficiently absorbing and dissipating energy. As a result, buildings are able to protect both occupants and critical structural elements, ensuring stability even during extreme events. 2. Base isolation systems. Base isolation is another technique used to decouple a structure from the ground motion during an earthquake. By introducing flexible bearings or isolators between the building foundation and superstructure, base isolators allow for relative motion between the structure and the ground. Challenges. For buildings located in seismic regions, base isolators are designed to absorb and dissipate energy from earthquake ground motions. Advanced analysis. Using tools like finite element analysis, FEA, engineers simulate the building's performance with base isolation under seismic loading. The isolators are designed with materials like rubber or steel, often combined with viscous dampers to enhance energy dissipation. Outcome. Base isolation can greatly reduce the acceleration and displacement experienced by the building, leading to lower structural damage during an earthquake. Notable examples include hospitals and critical facilities, where uninterrupted functionality is vital after a seismic event. 12.2. Energy absorption in blast and impact loading. Structures subject to blast loads or vehicle impacts, e.g., terrorist attacks, industrial accidents, or vehicle collisions, must be designed to absorb significant amounts of energy while preventing catastrophic failure. Energy-absorbing elements are incorporated into the structure to ensure the building remains intact and functional after an impact. 1. Blast load mitigation in building design. Case study: blast protection for government buildings. Challenges. In high-security buildings, such as government facilities or embassies, blast-resistant design is critical for protecting occupants and minimizing damage to critical infrastructure. The building's structure must be able to absorb the energy from explosions without collapsing or suffering severe damage. Advanced design. Engineers use blast load analysis to simulate the effects of explosive forces on structures, assessing both the structural response and the damage potential. Blast-resistant windows, reinforced concrete walls, and energy-absorbing barriers are common features. These systems are designed to absorb the blast energy, reduce structural deformation, and prevent catastrophic collapse. Outcome. Blast-resistant designs help protect buildings from explosive impacts by distributing the blast force and absorbing energy through inelastic deformation. The goal is to preserve structural integrity while minimizing injuries and damage. These systems are regularly tested through simulated blast events and structural impact analysis using advanced software like Abaqus and LSDyna. 2. Impact protection systems for bridges. Bridges are critical infrastructure that must withstand the effects of vehicle impacts, flooding, and seismic events. Energy absorption systems, such as crash barriers and shock absorbers, are designed to protect bridges from accidental collisions and minimize the damage caused by such impacts. Challenges. A bridge needs to absorb impact energy from vehicular collisions, such as those from trucks or railroad cars, without failing structurally. Advanced design. Crash barriers are designed using energy-absorbing materials like high-tensile steel, concrete, and composite materials that deform upon impact. Advanced analysis methods, including finite element impact simulations, are used to optimize the design and ensure energy dissipation while preserving the integrity of the bridge structure. Outcome. These energy-absorbing systems reduce the kinetic energy transferred to the bridge, minimizing structural damage and improving safety for travelers. Additionally, impact-resistant materials help prevent long-term degradation from repeated low-intensity impacts. 12.3. Safety considerations in energy-absorbing design. Incorporating energy-absorbing systems into structural designs helps improve safety in several ways. 1. Protection against structural failure. By absorbing and dissipating energy, structures are less likely to experience catastrophic failure during extreme events. This improves occupant safety, reduces damage to critical systems, and helps maintain the structure's operational integrity. 2. Minimizing human injury. The primary goal of energy absorption is to reduce the amount of energy transmitted to the occupants of the building or structure. Damping systems and shock absorbers ensure that structural deformations remain within safe limits, preventing injuries caused by excessive movement or collapse. 3. Preventing progressive collapse. Advanced energy-absorbing systems also help prevent progressive collapse, domino-like failures, by ensuring that the energy from localized impacts or seismic shaking is absorbed and dispersed, preventing failure from propagating throughout the structure. Energy absorption systems are a critical component of modern structural design, ensuring the safety and integrity of structures subjected to dynamic loads such as earthquakes, windstorms, blasts, and impact events. Advanced structural analysis and simulation tools like finite element analysis, FEA, nonlinear dynamic analysis, and impact modeling allow engineers to predict the performance of energy-absorbing systems under extreme conditions and optimize the design for both safety and performance. Whether it's designing a seismic damper for a skyscraper or a blast-resistant barrier for a government building, energy absorption ensures that structures remain intact during catastrophic events, thereby protecting both people and infrastructure. As the need for resilient designs increases, advanced structural analysis methods continue to play a crucial role in ensuring that energy-absorbing technologies are effective in enhancing safety and sustainability in extreme environments. 13. Conclusion. Key takeaways from the course. Throughout this course on advanced structural analysis, we have covered a wide range of critical topics, all aimed at equipping engineers with the knowledge and tools necessary to design and analyze complex structures. Here are the key takeaways from the course. 1. Advanced structural analysis is essential for modern engineering. As engineering projects become increasingly complex, understanding and applying advanced structural analysis methods is essential. Whether it's the design of skyscrapers, bridges, or infrastructure subject to dynamic loads like wind, earthquakes, or impact, the ability to analyze and predict structural behavior is fundamental to ensuring the safety and performance of these systems. Key tools and methods. Matrix methods, finite element analysis, FEA, plastic analysis, and energy methods are essential in performing advanced structural analyses for real-world engineering challenges. Structural integrity. Engineers need to ensure that structures can withstand the forces and deformations that occur due to external loads such as seismic or wind forces, as well as material limitations. 2. Understanding of structural behavior under various load conditions. A major focus of the course was on understanding how structures behave under different types of loading conditions. Key concepts covered include static versus dynamic loads, understanding how structures respond to both static, e.g., dead and live loads, and dynamic, e.g., wind, seismic, and impact loads. Forces is critical. These forces can cause both immediate and long-term effects on the stability and performance of the structure. Seismic and wind load design. Engineers must account for natural hazards like earthquakes and extreme weather. Through techniques such as response spectrum analysis, time history analysis, and wind load analysis, engineers can predict the response of structures and design them to withstand these dynamic loads effectively. 3. Advanced methods for structural analysis. Several advanced methods discussed in this course play a significant role in enhancing the precision and efficiency of structural analysis. Matrix methods. These methods, including the stiffness matrix and the global stiffness matrix, are essential for analyzing complex structures like frames, trusses, and space structures. These methods allow for more accurate predictions of structural displacements and internal forces. Finite element method, FEM. FEM is a powerful tool used for modeling complex structures, enabling engineers to simulate behavior under different loading conditions. This method is especially useful in dealing with nonlinear behavior in geometrically complex structures. Plastic analysis. The concepts of plasticity and yielding allow for analyzing structures under ultimate loading conditions, helping engineers understand collapse mechanisms and optimize designs for indeterminate structures. 4. Real-world applications. The principles of advanced structural analysis are not just theoretical, they have significant real-world applications. These methods are used in bridge and tall building design, ensuring that bridges and skyscrapers can resist both static and dynamic loads. Advanced analysis techniques help design these structures for safety and long-term durability. Seismic and wind load design. The application of advanced methods ensures that structures are designed to withstand natural disasters. Whether it's the use of tuned mass dampers for skyscrapers or base isolation for seismic resistance, the dynamic analysis is essential to meet safety and performance standards. Energy absorption and impact protection. Energy-absorbing elements like dampers and shock absorbers are integral in ensuring that buildings, bridges, and critical infrastructure can absorb and dissipate energy from dynamic forces, such as blasts and impacts, ensuring occupant safety and structural integrity. 5. The importance of computational tools and software. In today's engineering world, computational tools and structural analysis software, e.g., SAP 2000, ETABS, ANSYS, are indispensable. These tools allow engineers to model and simulate complex structures, perform dynamic analysis for earthquake, wind, and impact loads, optimize designs for cost-effectiveness, safety, and efficiency, automate calculations and analyses, reducing errors and increasing design accuracy. Having a strong understanding of how to use these tools and interpret their results is crucial for modern structural engineers. 6. Future directions and trends. As engineering practices evolve, so do the techniques for structural analysis. Some future directions and trends include nonlinear structural analysis. With advancements in materials and more complex loading conditions, nonlinear analysis is becoming increasingly important to predict the behavior of structures under large deformations or material nonlinearity. Sustainability and green design. With increasing attention on sustainable design, engineers are now tasked with designing structures that are not only safe and efficient but also eco-friendly. Advanced methods are being applied to reduce material usage, optimize energy efficiency, and create more sustainable structures. Smart structures. The integration of smart materials and sensor technology will allow structures to self-monitor their health, making predictive maintenance possible and extending the lifespan of the structure. 7. Further reading and resources. As you continue in your career or studies in structural engineering, there are numerous resources to further enhance your understanding of advanced structural analysis. Suggested further reading includes Structural Analysis by Russell C. Hibbler, a comprehensive textbook covering both classical and advanced methods in structural analysis. Introduction to the Finite Element Method by J.N. Reddy, a textbook dedicated to the detailed study of the finite element method. Research journals. Regularly reviewing journals such as the Journal of Structural Engineering and Structural Safety will keep you updated on the latest advances in the field. By the end of this course, you should now have a deeper understanding of advanced structural analysis techniques and how they are applied to real-world problems. Whether you're designing a bridge, a skyscraper, or a complex industrial structure, these methods will help you ensure that your designs are safe, efficient, and resilient. The knowledge gained in this course will be invaluable as you move forward in your career, and it will provide the foundation for exploring even more specialized topics in structural engineering. With advanced tools, methods, and a deeper understanding of how structures behave under a variety of conditions, you are well equipped to tackle the engineering challenges of the future. 13. Conclusion. Future trends in structural analysis. As technology and engineering practices continue to evolve, so do the methods and tools used in structural analysis. The future of structural engineering is shaped by advancements in computational techniques, materials science, sustainability, and the increasing complexity of the structures we design. Here are several key trends and developments that will drive the future of structural analysis. 1. Integration of artificial intelligence and machine learning. In the future, artificial intelligence, AI, and machine learning, ML, are expected to play a significant role in the field of structural analysis. These technologies can enhance how we analyze, optimize, and predict the performance of structures. AI-driven optimization. AI can help identify the most efficient structural designs by analyzing vast amounts of data and running simulations to propose solutions that human engineers may not easily consider. Predictive maintenance. Machine learning algorithms can predict when structural components are likely to fail based on real-time data, enabling predictive maintenance and enhancing the lifecycle management of structures. For example, AI could analyze the performance of buildings and predict structural health over time, allowing engineers to take preventive measures before catastrophic failures occur. 2. Advancements in computational power and software. The continuous development of computational tools and analysis software will further revolutionize structural analysis. Real-time structural analysis. Future advancements in computational power will enable engineers to perform real-time structural simulations during construction, allowing for immediate feedback and adjustments. Cloud computing and collaboration. Cloud-based software platforms will make structural analysis and modeling more collaborative, allowing teams across the world to work on the same models simultaneously. Integration with building information modeling, BIM. BIM and structural analysis software will become more integrated, allowing for seamless transfer of data between design, analysis, and construction phases. This integration will reduce errors, improve efficiency, and lead to better collaborative workflows. 3. Nonlinear and multi-scale analysis. Future structural systems will require more complex analysis methods to predict the behavior of nonlinear materials and multi-scale phenomena. Nonlinear structural analysis. As structures become more sophisticated, engineers will need to account for nonlinear material behaviors such as plastic deformation, creep, and fatigue. This is especially important in extreme events like earthquakes, windstorms, or blast loads where structures may undergo significant inelastic deformations. Multi-scale modeling. Engineers will increasingly adopt multi-scale analysis, where microscopic material behaviors, e.g., at the level of fibers or grains, are integrated with macroscopic models of the entire structure. This will help design materials with optimal properties, ensuring better performance under complex loading conditions. 4. Smart and adaptive structures. As we face more challenges related to climate change, sustainability, and extreme events, smart structures will become more common. These structures will integrate advanced technologies that enable them to respond adaptively to external conditions. Shape memory alloys, SMAS, materials such as SMAS that change shape in response to environmental conditions, like temperature changes or strain, could be used in structural components to make buildings and bridges more adaptable to dynamic loads. Smart materials and sensors. Sensors embedded in structural components will allow buildings to monitor their own health, providing real-time data on deformation, stress, and vibration. This data can be used for adaptive design, allowing structures to adjust their behavior in response to changing conditions, e.g., wind loads, earthquakes, etc. Adaptive dampers. These systems will automatically adjust their damping characteristics to optimize energy dissipation during dynamic loading events, such as earthquakes and windstorms, ensuring structural stability. 5. Sustainability and green design. There is a growing demand for sustainable design practices in structural engineering. The need to design structures that are energy efficient, resource conserving, and environmentally friendly will drive the adoption of new materials, technologies, and methods. Eco-friendly materials. Sustainable construction materials, such as recycled concrete, carbon-reducing steel, and biodegradable composites, will become more common in structural designs. Future structural analysis tools will incorporate these materials to optimize designs based on both performance and environmental impact. Carbon footprint reduction. As the construction industry focuses more on reducing its carbon footprint, structural engineers will need to evaluate the environmental impact of their designs, incorporating methods to optimize material usage and reduce waste. Net zero energy buildings. Structural designs will integrate systems that help buildings achieve net zero energy by producing as much energy as they consume, with advanced structural analysis ensuring that the energy-efficient elements, like solar panels and wind turbines, are structurally feasible and safe. 6. Resilient infrastructure and climate adaptation. As climate change increases the frequency and severity of natural disasters, resilient infrastructure will be more critical than ever. Advanced structural analysis techniques will help design structures that can adapt to extreme weather events and evolving environmental conditions. Climate-resilient design. Engineers will use advanced simulation tools to model the effects of climate change on structures, considering rising temperatures, increased rainfall, storm surges, and flooding. This will allow for the design of flood-resistant, wind-resistant, and seismic-resistant structures that can withstand changing climate conditions. Infrastructure for extreme events. Coastal cities, earthquake-prone zones, and wind-swept regions will require infrastructure designed to withstand extreme events. This includes designing bridges, roads, and buildings with enhanced energy absorption and dynamic response to ensure they remain functional after such events. 7. Automation and robotics in structural construction. The integration of robotics and automation into the construction process will continue to transform how structures are built and analyzed. Automated construction. Robots and automated machinery will be used to construct and assemble components of a structure, potentially reducing human labor, increasing precision, and speeding up construction times. 3D printing. The use of 3D printing for concrete and other construction materials will allow for the creation of highly optimized and complex structural components. Structural analysis will be necessary to ensure these components can withstand the forces they will encounter. Drones for inspection. Drones equipped with sensors and cameras will be used to inspect structures and monitor their condition over time. This data can be integrated with structural analysis tools to predict maintenance needs and identify potential issues before they lead to failure. 8. Multidisciplinary integration in design. The future of structural analysis will involve a closer integration of different disciplines to create more holistic designs. Collaboration with environmental engineers. Structural engineers will work more closely with environmental engineers to ensure that structures not only perform well under loading conditions but also integrate well with the environment, reducing negative impacts and enhancing sustainability. Collaboration with urban planners. As cities grow and evolve, structural engineers will need to collaborate with urban planners to design infrastructure that meets the needs of growing populations while also considering long-term sustainability. The future of structural analysis is bright, with exciting advancements on the horizon. As engineers continue to push the boundaries of technology, materials, and design, structural analysis will become more accurate, efficient, and sustainable. The key to success will be the ability to integrate new technologies such as AI, machine learning, smart materials, and sustainable practices into traditional structural analysis methods. By embracing these future trends, engineers can ensure that our built environment remains safe, resilient, and adaptable in the face of dynamic challenges, creating structures that can meet the needs of a rapidly changing world. 13. Conclusion. Further reading and resources. As you continue your journey in structural engineering and deepen your understanding of advanced structural analysis, it is essential to engage with further reading materials and resources to enhance your knowledge. Below is a curated list of books, journals, and online resources to help you stay updated with the latest trends, technologies, and methodologies in the field. 1. Books on Advanced Structural Analysis. Structural Analysis, by Russell C. Hibbler. A widely used textbook that covers both classical and advanced methods of structural analysis. It offers clear explanations of various techniques with numerous examples and exercises to help solidify your understanding. Theory of Structural Analysis, by Ramaswamy and Mays. This book provides in-depth coverage of classical and modern techniques for analyzing structures, including matrix methods and energy principles. Introduction to the Finite Element Method, by J.N. Reddy. A comprehensive textbook focused on the finite element method, FEM, including its theory, formulation, and applications in structural analysis. Plasticity for Structural Engineers, by Wei-Fa Chen and Songping Dai. This book provides detailed coverage of plastic analysis, including concepts of yielding and collapse mechanisms, and is useful for those interested in advanced structural behavior under extreme loading conditions. Advanced Structural Analysis, by Aslam Kasimali. A specialized text on advanced methods in structural analysis, including matrix methods, finite element analysis, and more, with practical examples. 2. Research journals. Staying up to date with the latest research and innovations in structural analysis is essential for professionals. Here are some of the most influential journals in the field. Journal of Structural Engineering, ASCE. Published by the American Society of Civil Engineers, ASCE. This journal covers a broad range of topics related to structural analysis, design, and construction. Computers and Structures. Focuses on the computational techniques and software used in structural analysis and engineering design, including advanced modeling, simulation, and optimization methods. Structural Safety. A journal dedicated to the analysis of structural safety, reliability, and resilience, featuring research on failure analysis, design for extreme events, and risk-based design methods. Finite elements in analysis and design focuses on the finite element method, FEM, offering research articles on new developments in the theory, implementation, and applications of FEM to solve real-world structural problems. Journal of Earthquake Engineering specializes in the behavior of structures under seismic loading, earthquake-resistant design, and dynamic analysis techniques. 3. Online resources and websites. American Society of Civil Engineers, ASCE, Structural Engineering Institute, SCI. The SCI section of ASCE offers a wealth of resources, including technical papers, guidelines, and conferences that focus on the latest developments in structural engineering. ASCE Structural Engineering Institute, MIT OpenCourseWare, Structural Engineering Courses. The Massachusetts Institute of Technology, MIT, offers free online courses on various aspects of structural analysis and design, including advanced topics like FEM and matrix methods. MIT OpenCourseWare, Structural Engineering, Coursera and edX. Platforms like Coursera and edX offer numerous online courses in structural analysis, including advanced finite element methods, dynamic analysis, and more. Some notable courses are provided by top universities such as Stanford, Georgia Tech, and University of California, Berkeley. Structural engineering webinars and conferences. Many structural engineering societies, such as the International Association for Bridge and Structural Engineering, IABS, offer webinars, workshops, and conferences that feature the latest research, case studies, and applications in the field. Attending these events provides an excellent opportunity for learning and networking with professionals and experts. ResearchGate, a platform where academics and engineers can share their research papers, technical articles, and insights into structural analysis. It is a good source for keeping up with the latest publications and discussions in the field of structural engineering. ResearchGate, Structural Engineering. 4. Software and tools for structural analysis. As computational tools continue to evolve, proficiency in the software used for structural analysis is becoming a critical skill. Below are some popular tools and software used in the industry. SAP 2000, a versatile structural analysis and design software that provides a wide range of modeling capabilities, including static, dynamic, and seismic analysis of structures. ATABS, a building design and analysis software used extensively for modeling and analyzing buildings under static and dynamic loads, with advanced capabilities for handling tall building and seismic design. ANSYS, a finite element analysis, FEA, software that is widely used for structural, thermal, and fluid dynamics simulations. It is particularly useful for more complex nonlinear analysis and multi-physics simulations. Abaqus, a powerful FEM tool used for advanced structural analysis, including nonlinear and dynamic simulations, and applications in material modeling and structural optimization. OpenSys, an open-source software framework designed for simulating the behavior of structural systems under dynamic loads. It is especially useful for earthquake engineering and performance-based design. RISA 3D, a structural analysis and design software known for its 3D modeling capabilities, which is ideal for buildings, bridges, and other civil structures. 5. Professional organizations and certifications. American Institute of Steel Construction, AISC. The AISC offers numerous publications, certifications, and resources for professionals working in the field of steel construction and structural engineering. AISC website. Structural Engineers Association. C. Joining a local chapter of the Structural Engineers Association can provide access to specialized training, resources, and professional development opportunities in advanced structural analysis and design. See website. Certified Structural Engineer. Say. Consider pursuing a professional certification in structural engineering, such as the Structural Engineer. Say. License, which recognizes advanced competency in structural design and analysis. 6. Further study and advanced degrees. For those interested in pursuing advanced studies in structural analysis and related fields, consider enrolling in graduate-level programs, master's and PhD programs in structural engineering. Universities like Stanford, UC Berkeley, and MIT offer advanced degrees focusing on cutting-edge topics such as finite element modeling, nonlinear analysis, and seismic engineering. Specialization in computational mechanics or structural dynamics. Graduate programs and specialized courses in computational mechanics or structural dynamics can provide deeper insights into advanced modeling techniques used for complex structures. By exploring these resources and continuing your study of advanced structural analysis, you will develop a comprehensive understanding of the tools, methods, and principles necessary to excel in the field of structural engineering. The evolving landscape of technology, materials, and software presents exciting opportunities for the next generation of engineers to shape the future of structural design and analysis. Thank you for watching. On behalf of Triune Biblical University Global Extension USA, we want to extend our heartfelt thanks to each and every one of you who stayed with us till the end of this lecture. Your commitment to learning and your patience truly mean a lot to us. If you found this content valuable, we kindly ask that you like, comment, and share with others who might benefit from it. Your engagement helps us reach more people and continue providing educational resources that can make a difference in the world. For those of you who haven't yet subscribed, we encourage you to do so. By subscribing, you will be notified whenever we upload new content, ensuring that you stay up to date with our latest lectures, courses, and updates. Once again, thank you for being part of this learning experience. We look forward to having you join us for more insightful and inspiring sessions. Stay tuned and keep learning. Triune Biblical University Global Extension USA.